In this lesson, we want a review of complex numbers. All right, so I want to start out by talking about the imaginary unit I again. So we say I is equal to the square root of -1, and this is used to allow us to simplify when we have the square root of a negative number. So for example, if I had the square root of, let's say, -4, using the product rule for radicals, I could write this as the square root of -1 times the square root of 4, okay? I know that the square root of 4 is 2, so let me just go ahead and put the square root of -1 times 2 like this, and then I can replace the square root of -1, okay, since those guys match up with this I here, okay? So this can go right there. So this is I times 2, or you just write 2I, okay? So that's a way to simplify the square root of a negative number. Now also, let me erase all this, we can square both sides and come up with another definition. We could say that I squared is equal to -1. And we're going to use this all the time, okay? Now, using this imaginary unit, we can form what's known as a complex number. So the complex number in standard form is going to look like this. You're going to have A, which is your real part, plus B, which is going to be the imaginary part, times I, which is the imaginary unit, okay? So let me label this real quick. This A is called the real part, okay? And then the B here is called the imaginary part, okay? Now, some books will call BI the imaginary part. Just get with your book or your teacher in terms of what they want to do if you get this for vocabulary. Now, in terms of complex numbers, we don't often think about it this way, but if you just had the number, let's say 3, well, 3 is a complex number, okay? 3 is a complex number because I could always say 3 plus 0i. It's kind of like when you think about 3 as being a natural number, right? It's a whole number, and then it's an integer, and then it's a rational number. And the way you show it's a rational number is you go, okay, well, 3 is equal to 3 over 1, right? Those are the same. So this is, by definition, a rational number. So it's the same kind of trick here where we just say, okay, well, 3 is really equal to 3 plus 0i because this is just 0, and 3 plus 0 is still 3, okay? So this tells me that any real number that I'm working with is also a complex number. So the real numbers are a subset, okay, of the complex numbers. And if you have a complex number, okay, like let's say 4 plus 2i, this is called a non-real complex number. That's how you can differentiate between the two. Also, you can have something that's called a pure imaginary number. Let's say you just had the 2i part, okay, so this you could write as 0 plus 2i, which is just 2i. This is also a non-real complex number, but a lot of books will call this a pure imaginary number. Okay. Let's go ahead and look at some examples. We're just going to fly through these. Again, this is just stuff we've already seen. If you wanted to simplify the square root of something like -147, you would use your product rule for radicals. I would just put this -1 here times, you would try to factor this. Well, 1 plus 4 is 5. 5 plus 7 is going to be 12. I know that 12 is divisible by 3, so 147 will be divisible by 3. And if I divide 147 by 3, I'm going to get 49. So I can put a 3 here, and I can get a square root of 49 here, okay? And this guy is a perfect square. So the square root of 49 is 7. So what I can do here is say that this is equal to square root of -1 times square root of 3, okay? Then times 7. Now this guy right here I can always replace with I. So really I'll end up with just saying that I have 7i, okay, times the square root of 3. So this would be our simplified answer for this square root of -147. Again, 7i times the square root of 3. All right, another similar problem, we have the square root of -180. So for this guy, if I think about 180, I would factor this. So 1 plus 8 is 9, so I know it's divisible by 9, so let me go ahead and put 9 there, and this would be 20, right? So 9 is 3 times 3, those are prime. 20 is 4 times 5, 4 is 2 times 2. So what I'd want to do, since 9 is a perfect square and so is 4, multiply those together, you have 36. So basically you'd want to write this as square root of -1 times square root of 36 times square root of 5. Okay, so that's going to allow you to simplify. And basically square root of 36 is 6, and square root of -1 is I. So I'm just going to put that we have I times 6, or I should really rearrange this and put 6i, and then just times the square root of 5. Okay, so simplifying these types of problems, very, very simple. This is our answer. Again, the square root of -180. This is going to simplify to 6i times the square root of 5. All right, so additionally, you will see complex numbers when you work with equations such as a quadratic equation. We know that if the discriminant, that b squared minus 4ac part, if that's less than 0, you're going to get complex solutions. okay? So we're going to see that here. So I'm just going to solve this. I'm going to use the quadratic formula. If you want to complete the square, you can do that on your own. So I have 2x squared plus 10x plus 5 equals 8x. I'm going to subtract 8x away from each side to put this in standard form. So this is going to cancel over here and be 0. So I'm going to have 2x squared plus 2x plus 5 equals 0. And basically, I'm going to record the values for a, b, and c. Okay, so what's a? It's the coefficient for x squared. So this guy right here, so that's a 2. And then what's b? It's going to be the coefficient for x to the first power, so that's also a 2. And then what's c? That's going to be your constant term, so in this case, that's 5. Okay, and then you're going to plug in. So x equals, remember this is negative b, plus or minus the square root of b squared minus 4ac all over 2a. Okay, this is something I've memorized throughout the years. If you don't have this committed to memory, it's okay. Something you can really look up quickly. Okay, so I'm just going to scroll down a little bit, and I'm going to plug in. So x is equal to the negative of 2 plus or minus the square root of, you're going to have 2 squared minus 4 times 2 times 5. And all I'm doing is I'm just plugging in. Okay, this is over 2 times 2. So I plugged in for b, a, and c, and that's where we got this from. Now, let's just go ahead and solve this real quick. It's just a matter of punching this into your calculator. So x is equal to negative 2 plus or minus the square root of, you have 2 squared, which is 4, minus 4 times 2 is 8. 8 times 5 is 40. Go ahead and do 4 minus 40. That's going to be negative 36. And you can see because this part right here ends up being negative, you're going to have these complex solutions. Okay. Then this is over the 4 because 2 times 2 is 4. And then the square root of negative 36, you can say that is 6i, right? Square root of 36 is 6, and then square root of negative 1 is I. Let's come down here a little bit, and let's go ahead and say that x is equal to negative 2 plus or minus, I'll put 6i over 4. Now, we can factor out a 2, okay, and make this a little bit better. So let's go ahead and say x is equal to, let me pull this down here a little bit. I'll factor out my 2. I'll have negative 1 plus or minus 3i, okay? Then over 4. I'm going to cancel this with this and put a 2 here. So we'll say x is equal to, you have negative 1 plus or minus 3i over your 2. Now, if you want to write this in standard form for the complex number, then you could put this, we'll go ahead and do solution set notation. I'll put negative 1/2, okay, like this. And then I'll go plus or minus, we'll do 3/2 and then times I like this. Okay, so that's your solution set notation. Maybe I can make those brackets a little bit better. Let me try to make this one a little bit better like that. Okay, and of course, this is two different solutions, right? You have negative 1/2 plus 3/2 times I, and then you have negative 1/2 minus 3/2 times I. All right, let's start working on some operations with complex numbers now. So the first thing I'm going to do here is a simple multiplication problem. I'm doing this to draw your attention to a common mistake. So we know with the product rule for radicals, something like square root of a times square root of b, this equals the square root of ab. This only works when they're both not negative, okay? So if you try to do this here, you're going to end up with the wrong answer. So what you have to do when you have negatives involved like this, you have to convert them over, okay? Simplify first, and then go through a multiply. So what I would do here is I would say this is I times the square root of 3, then times, for this one, let me go ahead and write this out. So we'll have 2 times, I'm going to put the square root of negative 1 times the square root of 4 times the square root of 2, okay? Just so you can see what I'm doing. Square root of 4 is 2, so 2 times 2 is 4, okay? And then basically you would have square root of negative 1, which is I. So this becomes 4i times the square root of 2, okay? So from here now, if you multiply, you see that you have I times 4i, which is going to be what? That's going to be 4i squared, okay? Square root of 3 times square root of 2, we can write as the square root of 6. Now, what is I squared by definition? Remember, earlier we said this is negative 1, so you can say you have 4 times negative 1 times square root of 6, which is just going to be the negative of 4 times the square root of 6. Now, you'll notice if you didn't follow this formula, okay, and go ahead and convert this first, you would end up with the wrong answer, right? You would end up with a positive 4 times the square root of 6, which is not the correct answer. Okay, so you want to make sure you convert these over, simplify them first before you multiply. Okay, let's look at some addition of complex numbers. Really, really easy topic. To add two complex numbers, so for example, if I have a plus bi, and then I add this to, let's say, c plus di, okay? This is what? Add the real parts, so a plus c, okay? And then plus, you're going to add the imaginary parts, so we'll say b plus d, okay? And this is multiplied by I. That's all it is. If you were subtracting, okay, so if this was a minus, then this would become a minus, and this would become a minus, and that's basically it. Now, when you subtract things away, remember you can do addition of the opposite. So you could always go plus and then minus like this, okay? So if you want to do that, you can do that. Either way, your answer is going to be the same, okay? So let's go ahead and get rid of this, and let's work on this problem here. So we have 4 plus 2i plus we have negative 7 plus 7i. Okay, so what do? We add the real part, so 4 plus negative 7. Let me show this. So 4 plus negative 7, okay? And let me put a parenthesis there, and then plus. You add the imaginary parts, so 2 plus 7, so 2 plus 7, okay, then times I out here. And let's go ahead and simplify this. So 4 plus negative 7 is negative 3, and then plus 2 plus 7 is 9, and then times the imaginary unit I. So this is your answer here, okay, and it's in standard form, so negative 3 plus 9i. All right, for the next problem, let's do a subtraction. So you can do this as addition of the opposite if you want. So I'm just going to go ahead and say this is 7 plus 2i, okay. I'm going to say plus, and I'm going to change the sign of everything inside. It's just like if I put a plus here and a negative 1 outside and distributed this to each term, okay? That's all I'm doing, okay? I think it makes it a little bit simpler. So I'm going to change this to positive 5, and I'm going to change this to positive. I'm going to write a 1 and then times I. Remember, if something's hanging out by itself like x, you can put a 1 in front as the coefficient, okay? So now I can just add. So this will be 7 plus 5, okay? And then plus, you're going to have 2 plus 1, okay, and then times I. So this gives me 12 plus 3i as a result. And again, if you want to do this with subtraction, you can. It's going to look a little bit different. So what you can also do is you can say that you have 7 minus, in this case, this is a negative 5, so be very careful, okay? And then you have plus, you're going to have 2 minus, this is a negative 1, so again, be careful, okay? And then times I here. 7 minus a negative 5 is 12. And then plus 2 minus the negative 1 is 3, and then times I. So same answer either way. I think it's more straightforward if you do addition of the opposite. Let's look at some multiplication. Again, with these type of problems, you can generally use FOIL, okay? And sometimes you'll get longer ones just depending on the situation, but just pretend like you're multiplying polynomials, okay? So I'm going to use FOIL here. So I'm going to do the first terms. Negative 4 times 2 is going to be negative 8. And then my outer, negative 4 times 4i would be minus 16i. My inner, I would do negative 3i times 2. That's minus 6i. And then my last, I would do negative 3i times 4i, which would be negative 12i squared. Okay, so I squared is negative 1, so let's go ahead and replace that. So I'm going to have negative 8, and then I'll go ahead and move this down and say minus 12 times negative 1. Well, negative times negative is positive, so I might as well just say this is plus 12. Okay, and then I have this negative 6i minus 6i. So I can say that's minus 22i. So negative 8 plus 12 is 4. And then we'll say minus my 22i. Okay, so that's going to be my answer there. And I boxed it off a little bit too closely. So 4 minus 22i. All right, so we should know at this point about conjugates. If you have complex conjugates, the formula is a little bit different. So if we have something like a plus b times a minus b, we know this is a squared minus b squared. Okay, as an example, let's say I have something like x minus 2, okay? Then I have x, let's say, plus 2. I know this is x squared, which is the first guy, minus 2 squared, which is the second guy, which is 4, okay? I don't need to FOIL this out. That's the quicker way to do it. But if I'm dealing with complex conjugates, the sign is going to change. It's not going to be minus, it's going to be plus. So for example, if I have a plus bi times a minus bi, what happens is a times a is a squared. The outer and the inner are going to cancel. And then the last, you have your minus b squared times I squared. Well, this I squared here is negative 1, and that's what's changing the sign. So you end up with a squared plus b squared, okay? So if I look at this pattern here, I have 4 plus 3i times 4 minus 3i. I can just say, okay, the first guy squared, 4 squared is 16, plus this 3 guy here, the second guy, just the b part, just the imaginary part. So the 3 guy squared, which is 9, so that's 25, okay? This is always going to be just a number. So in this case, it's just going to be 25, okay? Again, if you wanted to go through this the long way, we can. Just for the sake of completeness, we would do first times first. So 4 times 4 is 16. And then the outer would be negative 12i. The inner would be positive 12i. So you see those guys are still going to cancel. Then for the last, you have 3i times negative 3i. So that's minus 9i squared. And again, the I squared here is going to change the sign. And I circled that a little bit too widely. But basically this is what? This is 16, you might as well say, minus your 9 times negative 1, which is 16 basically plus 9, which again is 25. Okay, let's talk about dividing complex numbers now. So we know that if the imaginary unit I is in the denominator, since I technically is the square root of negative 1, it represents a radical and it needs to be rationalized, right? So we want to rationalize the denominator when we see this situation. So if I have something like negative 3 minus 4i over 5 plus 4i, what can I do? Remember, we just talked about multiplying by the complex conjugate. If I multiply this by 5 minus 4i over 5 minus 4i, what's going to happen is in the denominator here, I'm going to have a real number now, okay? We don't care what happens in the numerator. We're trying to get the radicals out of the denominator. So in the denominator here, again, I can just take this guy. 5 would be squared. That's 25. Then plus this 4 would be squared. That's 16. So this ends up being 41. Okay, so that's the denominator now. So we're good there. In the numerator, you go through and just do FOIL, right? So negative 3 times 5 is negative 15. The outside would be negative 3 times negative 4i, which would be plus, we'll go ahead and say 12i. The inside would be negative 4i times 5, which would be negative 20i. Let's just go ahead and combine like terms. This would be a negative 8i, so a negative 8i. So I'll put minus 8i there. And then for the last, you have negative 4i times negative 4i. That's going to be plus 16i squared. I squared is negative 1, so let's get rid of this and just change the sign. So basically, I have negative 15 minus 16. So let's say this is negative 31. So the top here is negative 31, and then I'll put minus 8i, okay? Now, of course, if you want to write this in standard form, you want to break this up and say that you have negative 31 over 41. Let me put equals here. So this is the real part, and then we'll put, you can put plus, negative, or you can just put minus. I'll put 8 over 41 like this, okay? Let me make that one a little bit better. And then I'll put my I out here, okay? So this is your A, or your real part. And then this is your B, okay, or your imaginary part, okay? Then you have your imaginary unit I. And of course, you could put plus negative there if you want to. That's up to you. If you put minus there, it's really the same thing, so that's why I'm putting that. Okay, let's talk about simplifying powers of I, which is a really easy concept. Once you realize, you go through this little cycle. So I, the first power is just I squared is equal to negative 1. I cubed is I squared times I, right? So this is negative 1 times I, which is negative I. And then I to the fourth power is I squared. Let me make that better. So I squared times I squared, which is basically what? Negative 1 times negative 1, which is 1. Now, using this pattern, it's really easy to rewrite things, okay, in terms of one of these guys right here, and then you're just going to simplify. Okay, you can put that as your answer. So this involves the rules of exponents. So what I'm going to do here is I'm going to look at this right here. So this number is 151, okay? So thinking about what number going down would be divisible by 4. So I just take 151, punch this into my calculator, divided by 4, gives me what? Well, you're going to get 37.75, but I'm going to write this as 37 with a remainder of 3, okay? So basically the 3 divided by 4 is where you're getting the 0.75 from. 37 times 4 is 148. So I can use that to my advantage. I can say, well, this is I to the power of 148 times I to the power of 3. So this is completely legal, right? I basically have just used my rules of exponents. We have I and we have I, so the same base. We would add exponents and we'd be right back to where we started. Now, what I can do, since this number right here is divisible by 4, I can use a little trick and I can say power to power rule, I to the fourth power raised to the 37th power, because again, 148 divided by 37 is 4. So 4 times 37 will be back to 148, right? This is power to power rule. Then times I cubed, okay? Now, why does this work? I to the fourth power, we see over here, is 1. So this guy right here is 1 raised to the 37th power. 1 to the 37th power. 1 to any power is always 1, right? So I can basically just get rid of this and say this is a big fat 1 now, times I cubed, okay? So I've dealt with that. And now I can just go to my little reference here and say, well, what's I cubed? It's negative I, okay? So that's basically what you want to do when you have a problem like this, when this guy's positive. All right, let's look at another example. So we have I to the power of negative 38. So there's a really easy way to do this, but let me do it the slow way first. I'm going to write this as 1 over I to the power of 38, okay? And then, of course, I can just do 38 divided by 4. and see where that puts me. It's going to be 9 with a remainder of 2, or 9.5. So really I could write this. I could say this is equal to 1 over I. I'm going to go ahead and put I to the 4th power raised to the 9th power, okay? Then I'll put times 1 over, we'll go ahead and say I raised to the power of 2, okay? That remainder right there. Now, we know that this guy right here is 1, and 1 to the 9th power is 1. So I can just keep going like this and say this is what? This is 1 times 1 over I squared. I squared is negative 1, so I can say this is 1 times 1 over negative 1. So this just ends up being negative 1. Okay, so really easy to simplify this, but this is kind of a long way to do it. The shorter way, if you're working with a negative exponent like this, well, now what I'm doing is I'm thinking about the smallest number that's divisible by 4, okay, that's going to be larger than this number. And I'm thinking about this in terms of its absolute value. So if you think about just the number 38, okay, going up, okay, what's the closest number that's going to be divisible by 4? Well, it's not 39, it's going to have to be 40, okay? So in other words, I would want to multiply this by, I would want to say I to the power of negative 38 times I to the power of 40. That's all I need to do, because what's going to happen here is that I to the power of 40 is just 1. I can multiply anything by 1, it's unchanged. So this is going to end up telling me that I have what? I to the power of negative 38 plus 40, okay, which is I to the power of 2, or I squared, which by definition is negative 1. So for me, this is a little bit quicker if I get this type of problem, but you can do it the other way if you'd like. All right, so the last thing I want to do is review a few things about the complex plane. So let's say we wanted to graph something like 5 minus 7i. What we do is set up a little complex plane. So instead of having x and y, we now have the imaginary, okay, which is vertical, and the real, which is horizontal. Okay, so before this was x and this is y. Now this is imaginary, this is real. Okay, so if I have something like 5 minus 7i, well, again, this is the real part. We talked about this earlier. And then this right here, the 7 is the imaginary, okay, part. So all I need to do is move 5 units horizontally. Okay, 5 is positive, so I'm moving to the right. So I'm going to go 1, 2, 3, 4, 5. Okay, so right there. And then I want to move 7 units down vertically. Okay, so I want to move 7 units on the imaginary axis going down because it's negative 7. So 1, 2, 3, 4, 5, 6, 7, and it's going to put me right there. Okay, so this is going to be my 5 minus 7i plotted on the complex plane. Okay, so the last thing would be the absolute value of a complex number. So if we have something like the absolute value of 2 plus 6i, again, remember the way you would do this, this is going to be the distance between this number and 0, or the origin on the complex plane. Okay, so your distance formula normally is what? It's the square root of, you have x sub 2 minus x sub 1 quantity squared, plus you have y sub 2 minus y sub 1 quantity squared. Well, one of the points is at the origin, right? So it's 0, 0. So this is 0, and this is 0. So this is 0, and this is 0. So really, I can simplify this and say the distance between this guy and the origin is the square root of, drop the x sub 2 and just say x squared, plus drop the y sub 2 and say y squared, okay? Now, in the terminology of complex numbers, instead of saying x squared, I'm going to say a squared. Instead of saying y squared, I'm going to say b squared, okay? So what I'm going to do is say that the absolute value of some complex number, let's say a plus bi, is equal to the square root of a squared plus b squared. So this is the square root of 2 squared, okay, 2 squared, and make that better, 2 squared, plus this guy would be 6 squared. So this is the square root of 4 plus 36, so it's the square root of 40, okay, which is square root of 4 times square root of 10, which in the end, let me get rid of this so I have some room to write this. In the end is going to be 2 times square root of 10. So this equals 2 times square root of 10, okay? If you want to see this graphically, you could plot this guy, this 2 plus 6i, on the complex plane. So 2 units to the right on the real axis, 6 units up on the imaginary axis. So that gives us this 2 plus 6i, so that's this guy right here. And then basically what I'm doing is just forming a right triangle, right? So this guy right here, okay, is going to be my hypotenuse. That's what I'm looking for, is the length of that guy. So this is the absolute value of the 2 plus 6i, the absolute value of that complex number. And again, if you look at this distance from here to here, let me circle this in a different color. So let me use this color here. So from here to here, well, this is 6 units, right? So this is 6 units. Let me put a 6 there. And then if you look at the distance from there to there, it's 2 units. So again, with the Pythagorean theorem, it's 2 squared plus 6 squared is going to be equal to, which in this case would be the absolute value of 2 plus 6i, okay? We might as well just say that's squared, right? The a squared plus b squared equals c squared. Well, if I take the square root of each side, well, then I'm back to my formula, okay, which gives me the square root of 4 plus 36, which is the square root of 40, okay? And again, we just simplify that, so we know that in the end, the absolute value of this 2 plus 6i is going to be 2 times the square root of 10, okay? So you can see that graphically or just from using your formula. In this lesson, we want to learn about adding complex numbers graphically. Also, we'll learn about converting between rectangular and polar forms. Okay, so our first topic of adding complex numbers graphically is very, very easy to do. As long as you understand how to add vectors, you're basically good to go. So we return to our complex plane, which remember is also called the Argand diagram. And basically we replace the x notation here for the horizontal axis with real. We replace the y notation for the vertical axis with imaginary. So if you have a complex number like a plus bi, okay, where again, the a is known as the real part, okay, and the b is known as the imaginary, okay, part. Well, basically, I could use this to plot a little point on this complex plane, okay? I'm going to go A units horizontally, okay, and I'm going to go B units vertically, okay? So if I had something like, let's say, 3 plus 7i, well, the coordinates, if you're thinking about this as working on your regular xy coordinate plane where you have some value here, comma, some value here, well, it's 3, comma, 7. Right? I'm just moving 3 units on the horizontal axis. Now it's called the real axis. And I'm moving up 7 units, okay, on the vertical axis, now called the imaginary axis. So 3 units to the right, 7 units up would put me right there, okay? So I would go ahead and label this as the complex number 3 plus 7i, okay? If you wanted to do another one, let's say we do something like -5, let's say minus 4i, okay? So the coordinates there would be -5, comma, -4. So I'm just going 5 units to the left on the real axis and then 4 units down on the imaginary axis. So right about there, let's go ahead and say this is -5 minus 4i. For the purposes of making sure that you understand how to do this, you should pull out a sheet of paper and just make a rough sketch of an Argand diagram. We're going to use it throughout the lesson, so you might want to have that handy. And go ahead and pause the video and try to just graph this guy. Think about where it would be on your complex plane. All right, so hopefully you gave that a shot. This -7 plus 6i, again, the real part's -7, so I'm moving 7 units to the left. The imaginary part is 6, so I'm moving 6 units up. Okay, so 7 units to the left, 6 units up, which would put us exactly right here. Okay, so this would be your -7 plus 6i. 7 units to the left and 6 units up. All right, now additionally, as you move higher in math, we start to think about graphing a complex number using vectors, okay? And specifically here, we're going to use a position vector or a vector in standard position, okay? So this just means that the initial point is at the origin. If you think about this in terms of a complex number, your origin is going to be at 0 plus 0i, or you could say 0, comma 0 if you want the coordinates, okay? So if the initial point's at the origin and the terminal point would be at this 8 plus 5i, so again, it's 8 units to the right and 5 units up, let's see this position vector graphically. So this would look something like this. Your initial point is at the origin, so right there. Your terminal point is at 8 plus 5i, so again, you're just going 8 units to the right and then 5 units up, and you have a directed line segment or a vector. Okay, so this is how we're going to show this 8 plus 5i when we're asked to graph it as a vector. All right, so now let's use the fact that we can graph a complex number as a position vector to show the sum of two complex numbers graphically. Okay, so we have this 6 plus 5i plus -9 plus 3i. Let's just add this together real quick just so we know what we're supposed to get, and then we'll go to the coordinate plane. So we know we would add the real parts, so we do 6 plus -9. Okay, that's your first step. Then plus, we would add the imaginary parts. So 5 plus 3, okay? And this is multiplied by the imaginary unit I. So what I want to do here is do 6 plus -9, that's -3. And then plus, you have 5 plus 3, which is 8. And then times the imaginary unit I. So -3 plus 8i is your resultant vector. Okay, so let's look at this graphically. And again, you can do this with the parallelogram method or the triangle method, whatever you want to do. But essentially, you'll see here that we have the origin here, okay, which is our initial point for basically everything. okay? So the 6 plus 5i, let's say you sketch that first. So here's the terminal point. Then you have this negative 9 plus 3i, okay? So if we sketch that guy, that's the terminal point. And then again, if you want to do the parallelogram method, this guy gets shifted down to make this side here, okay, to make this side here. This guy gets shifted down to make this side here, okay? And this point right here is going to be your terminal point for the resultant vector. You see you get the negative 3 plus 8i. Again, if you want to use the triangle method, you can do that as well. Basically, you're going to shift this guy down here. So you would have that vector going like that, okay? And you would have your triangle looking like that, okay? So whatever you want to do, you can just show this graphically. I prefer this method because this is what's shown in most textbooks. And basically, you're keeping in line with the fact that this is a position vector, and this is a position vector, and then this is your resultant vector. All right, so what we want to do now is move into writing a complex number in what's called the trigonometric form, also known as the polar form, okay? So typically, we see our complex numbers written as a plus bi, where again, the a is the real part and the b is the imaginary part, or some books will say bi is the imaginary part. So what we're going to do is just switch this over to the x plus yi, where x is now going to be the real part and y is going to be the imaginary part. Now, in terms of notation, you're going to sometimes see that the I is switched. So you might see x plus I times y. This is done for clarity. Sometimes you'll have a radical involved. So you just have to be very, very careful when you have I written like this to understand what the imaginary part is, okay? That I is always separate from that. You have to remember that. And I'll show you that specifically here with some examples. Now, in terms of getting this guy from what we call rectangular form, which is the form that you normally see it in, the a plus bi or the x plus yi, into this polar form, you need to consider a few things. So we've graphed this guy as a vector, a position vector to be specific. So the initial point is at the origin, 0, 0. The terminal point is at the complex number x plus yi, or you could say the coordinates here are x, y, okay, on the complex plane. So if you think about a few things, first off, the length or the magnitude of this vector is labeled as r. We've seen this a bunch of times where we think about, okay, well, the length of this guy is the absolute value of the complex number, okay? Going back, we said the absolute value of a plus bi is the square root of a squared plus b squared. Again, this is just the Pythagorean theorem, right? If I go through here and I think about how to get the length of this r or the magnitude of this vector, well, this guy here would be r squared is equal to the length of this, which is x, so x squared, plus the length of this, which is y, so y squared. A squared plus b squared equals c squared. We're just going back to the Pythagorean theorem. If I take the square root of each side, I get that r is equal to the square root of x squared plus y squared. Okay, so this is something we're going to need today. When we want to find our r value, we just use this little simple formula. Again, if you can't remember it, it's just the absolute value of the complex number. That's all it is. So let's go ahead and cut this away, and let's just paste this on this little sheet here. We'll just go back and forth. So we also need to know about a few other relationships. So we think about this angle theta here, this direction angle for our position vector. The cosine of theta is what? So the cosine of theta is what? Remember, it's adjacent, which is x, over hypotenuse, which is r. And then we can also say that the sine of theta is what? It's opposite, which is y, over hypotenuse, which is r. Okay, let's grab these and cut these away and paste these in here. Again, we're going to be using this in a second. And basically what I want to do is I want to solve these for x and y, okay? So to solve this for x, I would multiply both sides by r, and I would have x is equal to r times the cosine of theta. To solve this for y, I do the same thing. I'm going to multiply both sides by r, so I would have r times the sine of theta, okay? So we're going to use this in a little while. Let's go back up. There's one other thing we need. So we recall when we work with vectors, we figure out the direction angle theta using the tangent, right? So we say that the tangent of theta is equal to y over x, where x is not 0, okay? So we're going to use this as well. But again, you remember from working with vectors, you have to be really, really careful with the inverse tangent function, okay? With the inverse tangent function, you're going to get something in quadrant 1 or 4 only. 1 if your argument is positive, and 4 rotating clockwise if your argument is negative. So let's come in here and let's paste this in. And I guess we can put that about right there, okay? So the polar form, let me just start with the rectangular form. So we have x plus yi. If you want to write yourself a little note and say, okay, well, this is a plus bi, just to keep track of this. Again, x is the real part, just like a. Y is the imaginary part, just like b. Okay, that's all it is. Just a little notational change. So this is the standard form, or the rectangular, I can never spell that, form. Okay. Then if you want the polar form, we're going to do a little bit of work. So let me do this on another sheet, and I'll actually come back. So we have the x plus yi, and I'm just going to be plugging in for x and y. If I go back, you see that x is r times cosine of theta, and y is r times sine of theta. I'm just going to plug in. So r times cosine of theta will be plugged in for x, and r times sine of theta will be plugged in for y. So r times sine of theta, okay? So what I'm going to do here is say this is equal to, I'll have r times the cosine of theta. Then I'm going to put plus, I'm going to put r times sine of theta. And I'm going to wrap this in parentheses just for clarity. This is going to be multiplied by the imaginary unit I, okay? So again, this is x, this whole thing right here. And then this is y, this guy right here, and this multiplying the imaginary unit I, okay? So I'm going to go a step further and just factor the r out now. So let me put equals, and I'm going to come down here with this. Let me drag a little arrow down here. If I factored out the r, where would I be? I would have r times, inside of parentheses, I would have my cosine of this theta, and then plus, again, I pulled out the r, I would have my sine of theta. But what I'm going to do is I'm going to put the I out in front. So I times this sine of theta, okay? And you have to be very, very careful when I is written this way, because sometimes it's going to get mixed up. And again, I'll show you some examples where you need to be careful of this, okay? So this is your polar form. That's all it is. Some books will abbreviate this, and they will put R times CIS. It's an abbreviation. So the C, then you have the I, and then the S. Okay, so that's how you can remember. R times CIS, and then times the angle theta. Okay, so if you want to write it as R cis theta, or write it like this is more popular. This is your polar form. So let me write this up here. We have R times, you have your cosine of theta, plus I times your sine of theta like this. This is your polar form. Or again, some books are going to call this the trigonometric form. And the shorthand for this is R times CIS of theta. All right, let's just look at some examples of converting back and forth between the two. This is a very, very easy process, but you do need to work a few examples so you get used to things, okay? You'll also see a lot of these come up over and over again because they're using values on the unit circle. So what I have here is 2 multiplied by the cosine of 150 degrees plus I times the sine of 150 degrees. So this is in the polar form, right? You have some value R here, which in this case is 2. And it's multiplied by cosine of some angle theta, in this case is 150 degrees, plus I times your sine of some angle theta, okay? So all I would do here basically is figure out what is the cosine of 150 degrees, what is the sine of 150 degrees, basically replace things, and then use my distributive property to distribute the 2 into everything, and you're going to have it in the format of x plus yi, okay, just like you want. So first and foremost, what is the cosine of 150 degrees? Remember, this has a 30-degree reference angle, and we're in quadrant 2. Cosine is negative, okay? And the 30-degree reference angle, cosine of 30 degrees, is square root of 3 over 2. So I can say this is the negative of the square root of 3 over 2, okay? Then the sine of 150 degrees, same 30-degree reference angle, but again, I'm in quadrant 2, so sine is positive. This is going to be 1/2, okay? And positive 1/2 at that. So all I need to do now is just go through and basically replace things. Let me get rid of this. I think we don't need this anymore. I'll say that I have what? I'm just going to put equals here. I'll say 2 times. Here I'll put the negative of the square root of 3 over 2. And then plus, I'm going to put the I here, okay, times, I'll put my 1/2, okay? Be very careful with the I. Again, it gets switched around a lot. Sometimes it's here, sometimes it's there. Just be careful with it. So let's just erase this. We don't need it anymore. And now I'm going to distribute the 2 to each term inside the parentheses. So I would have 2 times the negative of the square root of 3 over 2. And then plus, I'll do 1/2 times 2. and then you can do times I, okay? So basically we see that this would cancel with this, and this would cancel with this. And in my rectangular form, I have the negative of the square root of 3, basically plus 1i, or you could just say plus I, okay? So this is my rectangular form, or my standard form. And again, this right here is the polar form, or some people call this the trigonometric form. All right, let's look at another one. So we have the polar form here. We have 6 times, you have the cosine of 135 degrees plus I times the sine of 135 degrees. So what is the cosine of 135 degrees? So again, you're in quadrant 2, so this is negative. What is the sine of 135 degrees? Again, you're in quadrant 2, so this is positive. Remember, 135 degrees, you have a 45-degree reference angle. So in each case, you're going to have square root of 2 over 2, right? This guy's just going to be negative because cosine, again, is negative in quadrant 2. And this guy would be positive, okay? So basically, I can replace this and say I have 6 times. This is going to be the negative of the square root of 2 over 2. And then plus I times, you're going to have the square root of 2 over 2, okay? So if I distribute the 6 into each term, I would have 6 times the negative of the square root of 2 over 2 plus I times, let me go ahead and switch the order here so this makes more sense. We'd have the square root of 2 over 2 times 6 and times I. And I'll just go ahead and cancel this. This cancels with this and gives me a 3. This cancels with this and gives me a 3. So basically I'm going to have the negative of 3 times the square root of 2. And then plus you'll have 3 times the square root of 2 and then times I. Now again, a lot of times for clarity, you're going to move this around. Let me drag this down here so it's a little bit better so you can see things. I'll erase that and put that back in. Instead of having the I here, most books will do 3i like this, then times the square root of 2. This is just to make it completely clear that the I is not under the square root symbol, okay? So the rectangular form here, or again the standard form, is negative 3 times square root of 2 plus 3i times square root of 2. And then again, your polar form, or the trigonometric form, is going to be 6 times this quantity, cosine of 135 degrees, plus I times sine of 135 degrees. All right, let's look at something more tedious now. So we're going to convert from our rectangular form to the polar form. I'm going to give you 3 easy steps for this. The first thing that I always do is I figure out what quadrant my complex number is in. You can do that by just thinking about the real part and the imaginary part. So in other words, if you were to graph this, again, on the complex plane, it's A comma B. So if this is positive and this is positive, then you're in quadrant 1, okay? If this is negative and this is positive, I'm going left and then up, so I'm in quadrant 2, okay? If they're both negative, I'm in quadrant 3, right? I'm going left and then down. And then lastly, if this is positive and this is negative, well, I'm going to be in quadrant 4, right? Because I'm going to the right and I'm going down. So just think about your real part and your imaginary part and ask yourself the question, if I was to graph this as a vector, okay, where would I be? Am I in quadrant 1, 2, 3, or 4? Okay, so that's the first thing you want to do. Now, if I look at this guy right here, I have 2 minus 2i times square root of 3. Again, this I is here for clarity. Okay, if you want to, you can write this as 2 minus 2 times square root of 3 times I. So it's crystal clear that this part right here is the real part, and this part right here, you can go ahead and take the negative with it, is the imaginary part, right? So A plus BI. Okay, so we know that the real part is 2, so that's positive. The imaginary part is negative 2 times square root of 3, that's negative. So I'm going to the right, okay, and then I'm going down. That means I'm going to be in quadrant 4, right? Because again, this is positive and this is negative, and you're thinking about this in terms of the complex plane. Okay, so now I know that theta is in quadrant 4. We need that for later on when we're getting our angle theta. So if we want to get this trigonometric form or the polar form, it's r times cosine of theta plus I times the sine of theta, okay? That's all it is. So I need to figure out what r is, and I need to figure out what theta is, and I'm done. So how do I figure out what r is? R, again, is just the absolute value of the complex number. Okay, we've been doing this forever. It's the square root of the real part squared, so 2 squared, plus the imaginary part. Again, if you're writing it like this, it's crystal clear. Negative 2 times square root of 3. So negative 2 times square root of 3, okay, this guy being squared. Some students make a mistake when it's written like this. Again, they put I in there for some reason. Again, just go ahead and write it like this so it's crystal clear that this is the imaginary part. You want the a squared plus the b squared, or the x squared plus the y squared, whatever the notation is, okay? The real part squared plus the imaginary part squared, okay? That's what you want. So we have r is equal to the square root of, this is 4, And then basically you have negative 2 squared, which is 4, and you have square root of 3 squared, which is 3. So 4 times 3 is 12. So I'd put plus 12 here, okay? So r is equal to the square root of 16, so r is equal to 4, okay? So the first part of that, okay, the first part of that is done. So r is equal to 4. And this looks like I made a radical here. I was just making a border. So let me kind of clarify that and put this maybe like this or something. That would be better, I think. And maybe I can just do it upside down. I'm just trying to make a border. That's not a radical. So r equals 4. Okay, so now I need to find theta. So what is that going to be? Again, you use the fact that the tangent of theta is y, okay, or the imaginary part, over x, or the real part, okay? So the imaginary part, you have your negative 2 times square root of 3 over your real part, which is 2, okay? So you can go ahead and cancel this with this, and this is the negative of the square root of 3, okay? Now what I would do, okay, is not punch this into the calculator as the tangent inverse of negative square root of 3, because you're going to get something in quadrant 4 rotating clockwise. Now, your teacher may allow that as an answer, but typically you want something between 0 and 2 pi, where 0 is included and the 2 pi is not, okay? So what I'm going to do is I'm going to say that I want the tangent inverse of the square root of 3. And this is going to give me 60 degrees, okay? This is going to be my reference angle, and I'm going to be in quadrant 4, okay? Remember, we figured out we're in quadrant 4 for this reason. So in quadrant 4, if I had an angle with a reference angle of 60 degrees, to find that I would do 360 degrees minus 60 degrees, which gives me 300 degrees, or in terms of radians, it would be 5 pi over 3. So now that we've done all this work, okay, we are ready to write this guy in polar form. And I guess you can get rid of this. We don't really need it anymore. I'm just going to write this and say that basically this guy, and I'll just even erase this, would be the r, which is 4, times you would have cosine of your angle. So you can use either one you want. You can do it in radians or degrees. So 300 degrees. And then plus, again, I'm going to put I first, and then times your sine, okay, of that same angle, 300 degrees. If you want to write this with radians, all it is, I'll put equals again, so 4 times, you're going to do cosine of 5 pi over 3, okay, and then plus I times the sine of 5 pi over 3. So always go with what your teacher says. If they want radians or degrees, just ask them, okay? So we basically have this done, and also if you wanted to, you can use that little abbreviation. Let me just show you that real quick. You could do, this is 4 times CIS. So again, the C, the I, and the S, that's where the abbreviation is coming from. And then times, let's just go ahead and say 5 pi over 3. All right, let's look at another example. So we have negative 2 times square root of 3 minus 2i. So again, the first thing you want to do is figure out what quadrant is theta going to be in. And again, you can speed this up at this point. Again, here's the real part. It's going to be negative. Here's the imaginary part. It's going to be negative as well. In other words, if you were to graph this, you would have negative 2 times square root of 3. This would be your location on the real axis. And then you would have negative 2. That'd be your location on the imaginary axis. So in other words, this is negative and this is negative. So I know I'm going to the left and down. So I'm going to be in quadrant 3. And I put equals here. I should just put is in quadrant 3. Okay, so we can keep that straight. Now, what I want to do is quickly find my value for r. I'm just going to make that a little bit more clean. So my quadrant 3, I'll just put for my angle theta. So for r, again, it's the absolute value of this complex number. However you remember it, remember it's the square root of the real part squared plus the imaginary part squared, however they're giving that to you, okay? So I'm going to take the square root of, I'll take negative 2 times the square root of 3 being squared, then plus I'll have my negative 2 being squared, okay? So from here, I know that basically negative 2 squared is 4, square root of 3 squared is 3. So 4 times 3 would be 12. And again, we already know this, so this is going to end up being 4, right? Because this is 12 plus 4, that's going to be 16. Square root of 16 is 4, right? But to go through the steps, this would be 4. Again, 12 plus 4 is 16. Square root of 16 is going to be 4. So r is 4, we know that. So let's find theta. This is the one that takes a little bit longer. So we know that tangent of theta, again, is y over x, or you could say b over a, if you think about this in terms of the traditional way we think about complex numbers. It's going to be the imaginary part over the real part. So the imaginary part is negative 2, so negative 2, and the real part is negative 2 times square root of 3. Okay, So this is going to cancel, and I'll have 1 over the square root of 3. If I rationalize the denominator there, so times the square root of 3 over the square root of 3, this is the square root of 3 over 3, okay? So basically, if I punched up the inverse tangent of square root of 3 over 3, I'm going to get something in quadrant 1. Remember, I'm looking for something in quadrant 3, okay? So let's go ahead and set this up. I want to go inverse tangent, okay, inverse tangent of square root of 3 over 3 like this. So you hit that up on your calculator, you're going to get 30 degrees, okay? And again, in quadrant 3, if I have an angle with a reference angle of 30 degrees, to find that, I would do 180 degrees plus 30 degrees, okay, which would give me 210 degrees. So theta is going to be 210 degrees. So now that we have all the required information, I can just put equals. I'm going to take my r value, which is 4, and I'm going to multiply by, again, you have your cosine of this angle, 210 degrees, plus I times the sine of this angle, which is 210 degrees. So that's basically it. That's your polar form. Now, if you want to write this with radians or write it as an abbreviation, you can keep putting equals. So 210 degrees in terms of radians would be 7 pi over 6. So you could say this is 4 times, you'd have the cosine of 7 pi over 6, plus I times the sine of 7 pi over 6. And again, one more time, this C, this I, and this S, you can use it to abbreviate. So you could say this is 4, and you go CIS or CIS, and then you'll say your angle. So again, you could do degrees or radians, whatever. We'll do 7 pi over 6. So another way to write it, this is the shorthand. All right, let's look at one more example. So we have the negative of the square root of 31 over 2 plus the square root of 93 over 2 times I. Again, just be careful. Sometimes they'll put the I up here because you're working with a radical. Just be able to separate the imaginary part from the real part. Okay, you need to know what those are, and you need to not get I mixed into that. Okay, so what I'm going to do here again is think about what quadrant am I going to be in. Okay, this is negative, this is positive, so I'm going to the left and I'm going up, right? So I'm in quadrant 2. So theta is in quadrant 2. Okay, very important to understand where I am. Now, once I understand that I'm in quadrant 2, again, when I go to find theta, okay, I'm going to basically get a reference angle and then use that in quadrant 2. Well, let's find r first because that's a little bit easier. So r equals, again, the square root of, take your real part being squared. So negative of square root of 31 over 2. We're going to square that, plus take this guy, the imaginary part, so the square root of 93 over 2, this guy squared. So r is equal to what? If I square this, I'm going to get 31 over 4. So the square root of, you'll have 31 over 4, plus this guy would be 93 over 4, okay? If you add those together, you're going to get 124 over 4. So 124 over 4, if you make that division, you're going to get 31, okay? You can't simplify that. 31 is a prime number. So basically, r is just the square root of 31, okay? So r is equal to the square root of 31. Okay, let's work with theta now. So the tangent of theta is what? It's the imaginary part, or y, or b, however you want to think about it. So square root of 93 over 2 over the real part, which is x, or basically a, however you want to think about that. I'm just going to flip this guy, because when you divide fractions, you multiply by the reciprocal. So I'll put the negative of 2 over the square root of 31. That's going to allow me to cancel this with this. I know that from the quotient rule for radicals, I can divide here. So 93 divided by 31 is 3. So I can basically say this is the negative, okay, the negative of the square root of 3. Now, we know from the first example, this guy is going to have a reference angle of 60 degrees. If I did the inverse tangent of square root of 3, I'm going to get 60 degrees. So because I'm in quadrant 2, what I want to do is I want to take 180 degrees, and I want to subtract the reference angle of 60 degrees, and that's going to get me to 120 degrees. So theta is 120 degrees here, okay? So theta is 120 degrees, or in terms of radians, you could say this is 2 pi over 3, okay? So basically, I'm ready to set this up. I can go ahead and say this equals, and let me just drag this out of the way. Put this down here. I'll say my r value, which is the square root of 31, times, let's just go ahead and use degrees first. So I'll say cosine of 120 degrees plus I times the sine of 120 degrees, okay? And again, you can keep going, right? So if you want to put this in terms of radians, I'll put equals, I'll do square root of 31 times the cosine of 2 pi over 3. and then plus I times, we'll do the sine of 2 pi over 3, okay, like this. And lastly, if you want to do your abbreviation, take your r value, which is square root of 31, and then times that CIS, or the CIS, again, the C, the I, and the S. So CIS, that's how you can remember that, and then times your 120 degrees. In this lesson, we want to talk about the product and quotient theorems. All right, so in the last lesson, we talked about how to write a complex number in what we call the trigonometric form. Most people call this the polar form. And here what we want to do is learn how to quickly multiply or divide two numbers if they're in polar form using something called the product or also the quotient theorems, okay? So I'm going to start off with the product theorem. And basically we have these two generic complex numbers written in polar form, right? Remember, when you think about the r value, if it's as a vector, if you think about it that way, this is the magnitude or the length of the vector, or you could also think about it as the absolute value of the complex number, okay? So that's the r value in each case. When you think about theta, okay, this is going to be, if you think about this as a vector, it's the direction angle, okay? Or if you think about it here, a lot of books will also call this the argument, okay? So you hear that terminology. So here we have this r sub 1 times the quantity cosine of theta sub 1 plus I times sine of theta sub 1. Okay, then times we have this other complex number, so r sub 2 multiplied by the quantity cosine of theta sub 2 plus I times the sine of theta sub 2. Okay, so all I need to do to derive my little product theorem, okay, is just use some FOIL. So I'm going to start out by multiplying r sub 1 times r sub 2. So r sub 1 times r sub 2. Then I'm just going to set up some brackets here, and I'm going to put these two inside. So I'm going to go the cosine of theta sub 1 plus I times the sine of theta sub 1. And then I'm going to go cosine of theta sub 2, and then plus I times the sine of theta sub 2, okay? So all we're going to be doing is FOIL, nothing fancy here. So I'm going to put equals r sub 1 times r sub 2, and then let me open up these brackets. And if we're doing FOIL, we're going to do the first term, so this guy times this guy. So this would be my cosine of theta sub 1 times the cosine of theta sub 2. Then I want to do my outer, so this one times this one. Let me go ahead and put plus. I have an I there. Let me put that out in front. And then I'll just do my cosine of theta sub 1 times my sine of theta sub 2. Okay? I'm going to put this down here because it's going to run off. So I'm going to put plus, and I'm going to erase this and this, and now we're doing the inside, right? So it's basically going to be, and let me change the color, this one times this one. So you would have I times the sine of theta sub 1 times the cosine of theta sub 2, okay? And then lastly, we have the L, right? So this guy times this guy. I times I is I squared. Now you can put plus I squared, but remember this is negative 1 by definition, so we're going to change this in a moment. Then you have your sine of theta sub 1 times your sine of theta sub 2, okay? Let me close the brackets there because this is being multiplied by all of those. Now, as I just said, I squared is negative 1, so we can erase this and just put a negative sign here, okay? And now what I want to do is I want to group everything where the terms that have an I are next to each other and the terms that don't have an I are next to each other. So I want this one and this one to be next to each other. And then let me change my highlighter color here. I want this one and this one to be next to each other. Okay, so let me go ahead and do that real quick. I'm going to put equals r sub 1 times r sub 2, and then inside the brackets here, I'll go cosine of theta sub 1 times cosine of theta sub 2, and then I'm going to do minus, I'm going to go sine of theta sub 1 times sine of theta sub 2, okay, and then we'll go ahead and say plus, let me scroll down and get a little bit of room here. I'll say I times the cosine of theta sub 1 times the sine of theta sub 2. And then I'm going to put plus, I have my I times the sine of theta sub 1 times the cosine of theta sub 2. Okay, so let me close the brackets there. Now, the reason we group these guys together is because to further simplify this or to get it into the form you're going to see in your book, you're going to use an identity. So if we go back to our little handout and we go to the sum and difference identities, I want to call your attention to this first one. So we have the cosine of some angle A plus some angle B. Okay, in our case, it's theta sub 1 and theta sub 2. Okay, so the cosine of A times the cosine of B minus the sine of A times the sine of B, okay? So what we have is this guy on the right, and we want to transform it to what it shows on the left, okay? That's perfectly legal. So what we're going to do is say the cosine of theta sub 1 times the cosine of theta sub 2, so this is like having A and B, okay, minus the sine of theta sub 1 times the sine of theta sub 2. Well, we could write that as the cosine of, we'll have the theta sub 1 plus the theta sub 2, okay? So I'm just using that identity to make this more compact. So let me put my bracket there. Let me put my r sub 1 times my r sub 2. Let me scroll down just a little bit to get some room here, okay? And basically, what I want to do now is for this second part, where I have, let me highlight this guy plus this guy, I'm first going to factor the I out, okay? So I'm going to put plus, let me do this over here, let me put plus, I'm going to put an I there. And inside, what I would have is the cosine of theta sub 1, okay, times the sine of theta sub 2. And then you'd have plus, you'd have your sine of theta sub 1 times your cosine. I probably can't fit this, so let me move this down here. Let me move this down here. So times the cosine, let me make this a little bit better. So the sine of theta sub 1 times the cosine of theta sub 2. So then let me close the bracket off here. So that's officially done, okay? And basically you see once I factor this I out, that here we can go back and we see that we have sine of A plus B is the sine of A times the cosine of B plus the cosine of A times the sine of B. Well, we have the same thing, okay? It's the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. Now, it's not in that order, okay? It's reversed here, but you could rewrite it, right? Because this is addition. So I could say the sine of theta sub 1 times the cosine of theta sub 2 plus the cosine of theta sub 1 times the sine of theta sub 2. Okay, it wouldn't matter. So let's go ahead and put equals. I'm going to rewrite that one as well. And I'll say that I have my r sub 1 times my r sub 2 inside of brackets. I'll have cosine of theta sub 1 plus theta sub 2. So then I'll say plus, I'll put my I here, and I'll do my sine of, I'll say my theta sub 1 plus my theta sub 2, okay? Let me close the brackets there. So this result here is what you're going to see when you look at your product theorem in your book, okay? So basically you multiply the two absolute values together. That's all you need to do. That's going to give you your r outside. And then inside, when you're working with this guy, you'd have the cosine of, you're adding the two arguments together. So now it's the theta sub 1 plus the theta sub 2 plus your I times sine of, again, you're adding your two arguments together. So your theta sub 1 plus your theta sub 2. So most books will just say you're multiplying the absolute values and adding the arguments if you want a simple way to remember that. Now, another way you might see this, again, in compact form, we might see this r sub 1 times the cis, or the cis, right? That comes from this, the cosine, the I, and the S, okay? It's an abbreviation. Let me just erase that. So basically, you have this r sub 1 times this cis, and I'll put theta sub 1. If it's multiplied by this r sub 2 times this cis, okay, and then theta sub 2, this is going to be what? Again, multiply these two guys together, these two absolute values. So this is r sub 1 times r sub 2, and then basically you would have your cis, and then you're adding these two arguments together, so your theta sub 1 plus your theta sub 2, okay? So this is the shorthand, probably a way easier way to remember it. All right, so to get things started, let's go ahead and take a look at a very simple example. We have these two complex numbers in polar form, and we just want to find the product. So we have 3 times this quantity. We have the cosine of 150 degrees plus I times the sine of 150 degrees. Then we're multiplying by, we have 3 times this quantity, cosine of 90 degrees, plus I times the sine of 90 degrees. So again, the very, very easy way to do this is just to multiply the absolute values together. So the absolute value of those complex numbers. So the 3 times the 3, that's going to give me 9, okay? And then I'm going to set this up. I'm going to go the cosine of, I'm going to add the arguments. So I'm going to add 150 degrees plus 90 degrees, okay? That's all I want to do. So the cosine of 150 degrees plus 90 degrees, okay? And then plus my I times, I'm going to do my sine of, it's the same thing, just adding the arguments. So 150 degrees plus 90 degrees. 150 degrees plus 90 degrees, okay? So basically, you're just going to simplify this, and I'm going to have 9 times, again, this quantity. Now it's going to be the cosine of 150 degrees plus 90 degrees is 240 degrees. So I'll say this is the 240 degrees plus I times the sine of, we'll say 240 degrees. And again, you can also write this using your abbreviation. So you could say that this is the 9 times the CIS, or the CIS, right? The C, and then the I, and then the S, and then go ahead and take that argument, the 240 degrees, okay, that angle there. So this is another way to write it. And then additionally, they might ask you to give it back to them in rectangular form. So let me just erase this, and this, and this, okay, and we'll do that real quick. So again, for rectangular form, you need to figure out what is this and what is this, and then you're going to distribute the 9 to each term inside the parentheses. So for a 240 degree angle, we have a 60 degree reference angle. So the cosine of 60 degrees is going to be a half, and the sine of 60 degrees is going to be the square root of 3 over 2, okay? But because I'm in quadrant 3, cosine and sine are both negative, so I can say that this is negative 1/2. And then for this one, I'll say it's negative square root of 3 over 2, so I might as well just say minus the square root of 3 over 2, and I'll just put my I behind here like this, okay? So from here, I'm just going to distribute the 9 to each term inside the parentheses. So I would have negative 9/2 like this, and then minus, the 9 gets distributed, so 9 times square root of 3 over 2, and then times the imaginary unit I. So of course, if they ask you for polar form, it's going to be this one, okay? And then if they ask you for the rectangular form, you need to go through and figure this out, and then you get this one. All right, so let's look at a slightly more tedious example. So what we're going to do here is we're going to have our complex numbers given to us in rectangular form. We're going to convert them into polar form just to get some practice. And then we're going to use the product theorem to find the product of those two complex numbers, okay? So what I'm going to do here, let me put equals. I'm going to convert this one into my polar form first. So to do that, my R value would be what? Remember, that's the absolute value of the complex number. So you're going to take the real part, which is negative of 2 times square root of 2, and you're going to square that. You're going to add that 2. You're going to have your imaginary part, which is also the negative of 2 times square root of 2, negative of 2 times square root of 2, okay, being squared, okay? So basically, if I think about negative 2 being squared, that's 4. The square root of 2 squared is 2. So in each case, you have 4 times 2, which is 8. So you're going to end up with 8 plus 8, which is 16, okay? So you basically have R is equal to the square root of 16, which is 4, okay? So I can say that R equals 4 here. Now for the argument, theta, or you could say the direction angle, if you think about this as a vector, the tangent of this theta is the imaginary part over the real part, right? The b over the a, or you could say the y over the x, however you think about this. So I'm going to take the negative 2 times square root of 2, negative 2 times square root of 2, over negative 2 times square root of 2. Well, this is basically going to be 1, right? So the tangent of theta equals 1. Okay. If we use our inverse tangent function, so tangent inverse of 1, what is this going to give me? Well, if I'm working with degrees, I'm going to get 45 degrees, okay? But this is not our answer, right? Because remember, we have to consider what quadrant we're in. This is just going to give me the reference angle. So in this particular case, this is negative and this is negative, right? So if I was to graph this complex number on the complex plane, I would go to the left and I would go down, right? So I'm in quadrant 3. So in quadrant 3, if I had a reference angle of 45 degrees, I would want 180 degrees plus 45 degrees, which would be 225 degrees. So theta here is 225 degrees, okay? So now that gives us the information to write this guy out. I can say that my R value is 4, and then my argument here, theta, is 225 degrees. So I'd have cosine of 225 degrees plus I times the sine of 225 degrees, okay? So the first one's done. Now we just need to do the second one. So again, let me put times here. For this one, the R value is the square root of, take the real part, so negative of the square root of 3. This is squared. Then plus, take the imaginary part. You can write a phantom 1 in there. This is really negative 1. So I'll put negative 1 here, and this will be squared, okay? So basically, the negative of the square root of 3 being squared is 3, and negative 1 squared is 1. So you're going to have 3 plus 1, which is 4. So R is the square root of 4, which is 2. Okay, so let's put 2 here. And then again, for the direction angle theta, I think about the fact that the tangent of theta is the imaginary part, which is negative 1, over the real part, which is the negative of the square root of 3. Now, let me go ahead and get rid of the negatives. So I'm just going to erase that from here. And I'm going to rationalize the denominator. So square root of 3 over square root of 3, multiply by that. And this gives me a tangent of theta, which is going to be the square root of 3 over 3, okay? Let me erase this and actually make this a little bit more compact. So the square root of 3 over 3. So again, if you punch this into your calculator, if you do tangent inverse of square root of 3 over 3, you're going to get 30 degrees, okay? But again, this is going to be your reference angle because this is negative and this is negative. So again, I'm in quadrant 3, right? If I want to plot that guy, I'd have to go to the left and go down. So in quadrant 3, if I have a reference angle of 30 degrees, to find that I have 180 degrees plus 30 degrees, that's 210 degrees. So my R value is a 2, okay? Put my parentheses there. I'd have cosine of, I would have theta is 210 degrees here, okay? So 210 degrees plus I times the sine of 210 degrees, okay? And again, you can use radians if you want. It's just a matter of what your teacher's working with. I'm just going to work with degrees here for now. Okay, so now to find the product, again, multiply the absolute values. So 4 times 2 is 8. And then I'm going to set this up. I'm going to go cosine of, I'm going to add the arguments. So 225 degrees plus 210 degrees. So 225 degrees plus 210 degrees, okay? Plus I times the sine of, again, I'm just going to add the arguments. 225 degrees plus 210 degrees. So 225 degrees plus 210 degrees. Okay, let me close that down. So we'll say this equals 8 times, okay? This quantity here is going to be the cosine of 225 degrees plus 210 degrees would be 435 degrees. So I'll say this is 435 degrees, and then plus I times sine of, again, that 435 degrees. Now, for some teachers, this answer is fine. For others, they want you to give an angle that is between 0 and 360 degrees, or 0 and 2 pi if you're working with radians, where in each case, the 0 is going to be included, and your 2 pi or 360 degrees is not going to be included, okay? So basically, you would subtract, since we're working with degrees, 360 degrees from each one of these to get your coterminal angle, and in this case, it's going to give you 75 degrees, okay? So I can say this is equal to 8 times the quantity, you have the cosine of 75 degrees, plus I times the sine of 75 degrees, okay? So just get with your teacher in terms of if you need to do that. Most books will go to this. Some books will leave it like this and say it's fine. So it's really up to your teacher. All right, now let's move on and talk about the quotient theorem. So again, I'm going to go through where this comes from. I know a lot of you find this quite boring, but it's good to be able to see where things come from. It also gives you a lot of practice with manipulating things. So let's say we had these two complex numbers in polar form, and now we want to do the division, okay? So we have this r sub 1 times the quantity cosine of theta sub 1 plus I times sine of theta sub 1 over r sub 2 times the quantity cosine of theta sub 2 plus I times sine of theta sub 2, okay? Let me set this up over here because we're not going to have room to do what we need to do. So this is r sub 1 times the quantity cosine of theta sub 1 plus I times, we have sine of theta sub 1. Okay, that's your numerator. Your denominator here, or what you're dividing by, your r sub 2 times the cosine of now theta sub 2 plus I times sine of theta sub 2. Okay, so the idea here is that you would multiply the numerator and denominator by the complex conjugate of the denominator. Remember, if you had something like a plus bi, the complex conjugate would be a minus bi. So here, you could go through and multiply, okay, the r sub 2 into each term, but you're going to end up factoring it back out. So all you really want to think about is the inside here, the terms are going to be the same, okay? It's just that the sign is going to be different. So what I'm going to do is I'm going to multiply by, I'm going to have this r sub 2, and then times the quantity, you're going to have cosine of theta sub 2, okay? So that's the same. This is going to be minus now instead of plus, and then the term is the same. So you have I times sine of theta sub 2. Again, the r sub 2 here would just be factored out if it was distributed in, so you can think about it as just being factored out there. Okay, so that's why it's out there. Okay, so I'm just going to write this in the denominator here. So r sub 2 and then cosine of theta sub 2 minus I times sine of theta sub 2, okay, like this. Now this is quite lengthy, so I'm going to do the numerator and denominator separately. The numerator is going to be very similar to what we did earlier. It's just that we're going to have a minus involved in some different places, so we're going to end up using some different identities. All right, so let's go ahead and attack the numerator and denominator separately. Let me copy this, and I'm going to go to a fresh sheet here, and let me just paste this in, okay, and my multiplication symbol's out of whack there. So if we go through here, again, we start this in a similar way to the last one. So r sub 1 times r sub 2, okay? And then inside of here, you would have this cosine of theta sub 1 plus I times the sine of theta sub 1, okay? And this would be cosine of theta sub 2. and then minus your I times your sine of theta sub 2, okay? So again, all we're going to be doing is some simple FOIL. So I'm going to go equals r sub 1 times r sub 2 like this. And I'm just going to FOIL things out. So first times first. So again, cosine of theta sub 1, and then times cosine of theta sub 2. All right, so the next thing we would do is the outer. So I would do this one times this one. So I'm going to put negative. I'm going to put my I out in front, and then the cosine of theta sub 1, and then times the sine of theta sub 2, okay? Then I'm going to go, let me erase this. Then I'm going to go the inside, so this one times this one. So I'll go plus, I'll have my I, and then the sine of theta sub 1 times the cosine of theta sub 2. Okay, so far so good. Now I just need my last, so let me go ahead and highlight. This one's already done, and then this one. So I know this is negative. I have I times I, which is I squared. And then I have the sine of theta sub 1, and then times the sine of theta sub 2. Okay, let me close the bracket there. All right, so remember, I squared is negative 1. So this is like if we had minus a negative 1, which is basically like having plus 1. Okay, so you can change this. You can change this to a big fat plus. Okay, so from here, now what I want to do is I want to get my terms with I together and the terms that don't have I together. So in other words, like we did before, this will be with this, okay? And let me color this differently. This will be with this, okay? So we're going to arrange it in that way. So let me go ahead and put equals here. Let me slide down just a little bit and get some room going. I'll have my r sub 1 times my r sub 2. I'm going to open up the brackets. So the cosine of theta sub 1 times the cosine of theta sub 2, okay? Then I'm going to put this next. So plus the sine of theta sub 1 times the sine of theta sub 2, okay? And then I'm going to put, you have a minus here and a plus here. It's actually to our advantage to rearrange that, okay? You can put it like this, but in the end, you can rearrange it because you're going to need an identity. So I'm just going to put this as plus. I'm going to use this one first. So I'm going to say I times the sine of theta sub 1 times the cosine of theta sub 2. And then I'm going to put minus the I times the cosine of theta sub 1 times the sine of theta sub 2. Now, you saw that last time we ended up factoring the I out. So let's go ahead and do that again. So I'm going to wrap this in parentheses, and I'm going to get rid of this, okay? And I'm going to wrap this in parentheses as well, okay? So now what I'm going to do is I'm going to go back, and I'm going to think about an identity that would help me out here. So I have cosine of some angle, let's call it theta sub 1, times cosine of some other angle, theta sub 2. Then plus we have sine of some angle, theta sub 1, times sine of some angle, theta sub 2. If we go back, you see that cosine of A minus B follows that pattern, right? Cosine of some angle A times cosine of some angle B, then plus sine of some angle A times sine of some angle B. So I can use that to rewrite this. I'm going to go r sub 1 times r sub 2, and then inside of brackets here, I'll have cosine of, I'll go ahead and say now this is the theta sub 1 minus the theta sub 2. Okay, so that part is done. Now, when we look at this one, sine of theta sub 1 times cosine of theta sub 2 minus cosine of theta sub 1 times sine of theta sub 2. If we go back, that's this guy right here, right? Sine of A minus B. This is sine of A times cosine of B minus cosine of A times sine of B. That's why I had to rearrange things, because it would have been this way, the minus first and the plus. You can always rearrange it, but it might not be obvious, so that's why I did that. So let's go back, and now let's write this as plus, don't forget the I, and then times your sine of, this is going to be your theta sub 1 minus your theta sub 2, okay? So go ahead and close this down. So this is your numerator. If you want to copy this, let me go ahead and copy this, and I'm back on this screen now, so let me come down a little bit. I'm going to put equals here, and let me go ahead and paste that in. And I already had an equals, so I'm doing it twice. So let me go ahead and move this over just a little bit. So I'm going to say this equals this. And actually, let me put this a little bit further down. And then I'm going to put this over. We now need to work on the denominator, okay? So let me go ahead, and actually I should probably have equals here to make this complete. And let me grab this denominator now. Let me copy it. Let's go to another sheet, and let me paste this in now, okay? And we don't need this, and I need a times here. Okay, so for this guy, what you need to realize is that you could first multiply your r sub 2 times your r sub 2. So that's going to give me r sub 2. I'm going to wrap this in parentheses for clarity. So this is going to be squared. And then we're going to have the cosine of theta sub 2 plus I times the sine of theta sub 2. Okay, then times the cosine of theta sub 2. now minus the I times the sine of theta sub 2. So notice that you have these complex conjugates here, okay, because you have the same term here and here, okay, and then you have the same term here and here, and this looks really weird. It looks like a face, so let me make that like that. And then basically your signs are different, okay? So what I would do here is just use my formula. So I would go ahead and say this is r sub 2 being squared times, essentially I would do the first guy squared. So let me put this inside of parentheses. I would say cosine squared theta sub 2, okay? And then minus your second guy being squared. So if I squared I would have I squared. If I squared sine of theta sub 2, I would have sine squared theta sub 2, okay, like this. Now, what are we going to do from here? Just think about this for a second. Minus I squared, remember this is negative 1. So this is basically like minus a negative 1, which is basically plus. Now hopefully you see this right away. You have cosine squared theta sub 2 plus sine squared theta sub 2. What is that? That's 1. If you go back, you see for the Pythagorean identities, sine squared theta plus cosine squared theta equals 1, right? So here we have cosine squared of theta sub 2, whatever that angle is, plus sine squared of theta sub 2, same angle, whatever it is, okay? And so this is going to be 1. So I can say this is r sub 2 being squared times 1, which just equals r sub 2 being squared, okay? So if I go back up, this is going to be my denominator. So let me bring this down here. And I'm just going to put this over r sub 2, and this is squared, okay? So remember, this is multiplication here. This is being multiplied. You could wrap this in parentheses to make that clear. This is being multiplied by this. So I can cancel a common factor of this guy with this guy. So essentially what I have here, okay, is going to be what you're going to see for your quotient theorem in your book, your r sub 1 over your r sub 2, okay? So you're dividing the absolute values, and then times this quantity here, you have your cosine of, you're subtracting the arguments, okay? So I'm doing my theta sub 1 minus my theta sub 2, okay? Then plus I times the sine of, again, I'm subtracting the arguments. So theta sub 1 minus my theta sub 2. And again, if you want to write this in a more compact form, well, if you had r sub 1 times your cis of theta sub 1 divided by r sub 2 times your cis of theta sub 2, okay? What this would be equal to is your r sub 1 over your r sub 2 times your cis of your theta sub 1 minus your theta sub 2, okay? So let me go ahead and wrap that in parentheses. And that's basically the shorthand. I think this is the easiest way to remember things. And let's just go ahead and look at an example. All right, so what we'll do here, we'll have this 2 times square root of 7 times the quantity. We have the cosine of 7 pi over 6 plus I times the sine of 7 pi over 6. And this will be over, you have your 3 times the quantity, you have your cosine of 11 pi over 6 plus I times sine of 11 pi over 6. So of course these two complex numbers are in polar form, so we can immediately use this quotient theorem, okay? But to get a little bit of extra practice, let's write our answer in polar form first, and let's also go into rectangular form, okay? So let's go ahead and say this is equal to, I'm going to divide the absolute values. So I'm going to say 2 times square root of 7 over 3, okay? This is going to be times the quantity. What you're going to do here is you're going to have your cosine of, you're going to subtract these arguments. So I'm going to do 7 pi over 6 minus 11 pi over 6. And I'll take care of this in a moment. I'll just leave it like this for now. And then plus I times your sine of, again, you're doing the same thing. So 7 pi over 6 minus 11 pi over 6. Okay, so just like that. All right, so let me close this down so that's proper. Let's put equals here. Let me scroll down and get a little bit of room going. So let's go ahead and say we have 2 times square root of 7 over 3. Okay, let me make that 3 a little bit better. And then inside of here, I'll have the cosine of, if I do 7 pi minus 11 pi, that would be negative 4 pi, right? You already have a common denominator. So let's say this is negative 4 pi over 6. And of course, you can reduce the fraction. Each is divisible by 2. So this would be 2 and this would be 3. So this is negative 2 pi over 3, okay? Then I'll do plus I times sine of the same thing, right? It'll be your negative 2 pi over 3. Let me go ahead and write this down here like this. And let me go ahead and close the bracket there, okay? So again, some teachers will accept this. Some of them want you to find the coterminal angle. So what I would do here is I could say negative 2 pi over 3 plus 2 pi, right? Or if I want a common denominator, this would be, multiply this by 3 over 3. So this would be 6 pi over 3. Okay, so 6 pi over 3. So your coterminal angle here would be 4 pi over 3. So you could really write this, and you could say that this is 2 times square root of 7 over 3. And then inside the brackets, I'll say this is the cosine of 4 pi over 3, okay, plus I times the sine of 4 pi over 3, okay? So for your rectangular form, what we'll do is we'll have 2 times the square root of 7 over 3. We need to think about the cosine, let me make a border here, the cosine of 4 pi over 3, okay? So this is going to be 240 degrees if you convert it into degrees. So cosine of 240 degrees, if that's easier for you. Again, it's going to have a 60-degree reference angle, or pi over 3 in terms of radians. So if you think about cosine of 60 degrees, again, it's a half, right? And this angle here, 240 degrees or 4 pi over 3, that's going to be in quadrant 3. So we know cosine is negative there. So this would first be the negative of a half. So let me put some parentheses here and say this is negative 1/2. Let me put plus my I so I don't forget it. If I think about the sine of 4 pi over 3, again, 60-degree reference angle, we know that it's going to be in quadrant 3. Sine is negative, so let me just go ahead and make that minus. And basically, pi over 3, the sine of that is going to be square root of 3 over 2, right? So it's the negative of the square root of 3 over 2. You can put the I out in front like this, or typically with this situation, I'll put it here. So we'll close that down now. And all I need to do is just distribute this inside to each term, right? So basically, I have 2 times square root of 7 over 3 times negative 1/2. And then minus, you'll have 2 times square root of 7 over 3 times square root of 3 over 2 times I, okay? So let's come down here and just simplify, and we'll have our rectangular form. So the 2's are going to cancel here. You'll have the negative of the square root of 7 over 3. And then minus, the 2's are going to cancel here. Square root of 7 times square root of 3 is the square root of 21. And then this is over 3, and of course times I. So here is your rectangular form if you're asked to give that answer. All right, for the last problem, let's go ahead and take a look at one that's a little bit tedious. So we have this 1 minus I times square root of 3. This is over. You have the negative of the square root of 14 over 2 minus, you have the square root of 14 over 2 times I. So you'll notice that this division here involves these two complex numbers in rectangular form. So what we're going to do is we're going to put these into polar form. We're going to use our quotient theorem, and we'll just leave our answer in polar form, okay? So let's start out by converting each one of these over. So I have 1 minus I times square root of 3. I'm just going to do this on a separate page. So 1 minus I times square root of 3. So the real part is 1. The imaginary part is the negative of the square root of 3, okay? So let's go ahead and say my R is going to be the square root of 1 squared, which is 1, plus the negative of the square root of 3 squared, which is 3. Okay, so obviously this is 4, and the square root of 4 is going to be 2. Okay, so let's put this as 2. Okay, so now I need to find my theta, right? So my argument for this guy. And so the tangent of theta is going to be equal to the negative of the square root of 3 over 1, okay? Might as well just say it's the negative of the square root of 3. So let me go ahead and do the inverse tangent function, okay, with the square root of 3. Forget about the negative. Let's punch that into the calculator. So what you're going to get there is 60 degrees, or pi over 3 if you want to work with radians. Let's work with radians since we work with degrees for the multiplication examples. So I'm going to say this is pi over 3, or you can just put 60 degrees if you like working with degrees. Okay, so let's put that there. Now, this is going to be my reference angle. Let's think about this guy. The real part here is positive, so I'm going to the right. And then the imaginary part here is negative, so I'm going down, right? So I'm going to the right and I'm going down. That means I'm going to be in quadrant 4. So what I'd want to do is I'd want to subtract 2 pi minus this pi over 3, okay, to figure out what my theta is going to be, okay? You can write this as 6 pi over 3. So 6 pi over 3. And this is going to give me 5 pi over 3, okay? Again, if you wanted to do this with degrees, you do 360 degrees minus 60 degrees, you would get 300 degrees. So however you want to do that. So let's go ahead and write this. Since we have all the required information, I'm just going to say theta here. Theta is 5 pi over 3, okay? So in polar form, we know that this is 2 multiplied by the cosine of this 5 pi over 3, and then plus I times the sine of our 5 pi over 3, okay? Again, if you want to put 300 degrees in there, feel free, okay? So I'm going to get rid of this. Let's go ahead and look at the other one. So we have this negative of the square root of 14 over 2 minus the square root of 14 over 2 times I. So let's go back. So we have the negative of the square root of 14 over 2, okay? Then minus, let me put this down here so it's a little bit more consistent. We have this square root of 14 over 2 times I. So my r is going to be equal to the square root of, I'm going to take this guy. So it's negative in each case. Just forget about it. We're going to be squaring it. Let's go ahead and say it's the square root of 14 over 2 squared. Well, if I square the square root of 14, I get 14. If I square 2, I get 4. So this is going to end up giving me 14 over 4, okay? So 14 over 4, which is going to be 7 over 2. So you would have 7 over 2, okay, plus 7 over 2, okay? So this would end up giving me 14 over 2, which is 7, okay? So this will be the square root of 7, okay? So that's all that is. So that's my r value. Let me drag this up here so it's out of the way. So now let's figure out what is the theta, okay? So again, if you look at this, the real part and the imaginary part, in each case is the same thing, right? So if I did tangent of theta is equal to, if you did the negative of the square root of 14 over 2, then over the negative of the square root of 14 over 2, that's just going to end up being 1, okay? So if I did the tangent inverse of this guy of 1, I get 45 degrees, or in terms of radians, it's going to be pi over 4. Okay, so you can put that, or you can put 45 degrees, whatever you want to do. So for this guy, this is negative and this is negative. So I'm in quadrant 3, right? I'm going to the left and I'm going down. So in quadrant 3, I would want to take pi, and I want to add pi over 4 to get that angle. So pi plus pi over 4, or again, you could do 180 degrees plus 45 degrees, whatever you want to do, okay? So for this one, I'm going to multiply this by 4 over 4. So this will end up being 4 pi plus pi, which is 5 pi, and then over the common denominator of 4, okay? So this is 5 pi over 4, or 225 degrees if you're working with degrees. So let's put 5 pi over 4 like this. Let's get rid of all this. So in polar form, this guy is going to be, we have our square root of 7 multiplied by, we're going to have our cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Okay, so this part's done. Let me copy this. Let's come back up to our problem, paste this in real quick. And I'm just going to get rid of this. And what I'm going to do is I'm going to put equals like this, and I'll just drag this over. And I missed something, so let me get all of this. Drag this over here. Let me put my little division bar, and I did that terribly. So let me try that one more time. And let me just scooch this down just a little bit so it lines up perfectly. All right, there we go. So now what I want to do is just use my quotient theorem. Okay, very easy at this point. So 2 divided by the square root of 7. So 2 divided by the square root of 7. Of course, you can rationalize the denominator there. I can multiply this by the square root of 7 over the square root of 7. So this is 2 times the square root of 7 over 7. So 2 times the square root of 7 over 7. So that's that part. That's done. And then basically what we want to do, times this quantity here, you have the cosine of, you're going to have 5 pi over 3 minus 5 pi over 4. And I'm making this terribly, so let me kind of edit this a little bit. So this is a 5 and this is a 4. And of course, we need a common denominator. Let's just stop and get this. So we need to go 3 and then 3. We need to go 4 and then 4. So this would be 20 pi over 12. This would be 20 pi over 12. Minus, it would be 15 pi over 12. So 15 pi over 12, okay? So this would give me what? It would give me 5 pi over 12. So the cosine here of 5 pi over 12. Then I'm going to have plus, I have my I times the sine of, again, it's the same thing. So the 5 pi over 3 minus the 5 pi over 4. So that gives us the 5 pi over 12, okay? So this is going to be our result in polar form. Again, if you wanted to figure this out in rectangular form, just evaluate the cosine of 5 pi over 12, evaluate the sine of 5 pi over 12, get those values, and then just use your distributive property here to set that guy up. In this lesson, we want to talk about powers and roots of complex numbers. All right, so in the last lesson, we talked about multiplying two complex numbers together when they're in polar form using something called the product theorem. So what we're going to do here is just go a step further, and we'll talk about these powers and roots of complex numbers. So what I'm going to do is I'm just going to start out with a simple complex number, something generic, in polar form. So I'm just going to write r times the quantity cosine of theta plus I times the sine of theta, okay? So remember, when we talk about r, that's the absolute value of the complex number. When we talk about theta, it's referred to as an argument, okay? If you think about the complex number as a vector, it's going to be the direction angle, okay? So let's say that I wanted to raise this to, let's say, the second power, right? So I'm squaring this, and basically what I would do here, I would just expand this, right? So this would be r times the quantity of the cosine of theta plus I times the sine of theta, okay? And I'm going to multiply by itself. So r times the quantity of the cosine of theta plus I times the sine of theta. So you can see here that you have r times r. Remember, you're multiplying the absolute values together. So this gives me r squared. Notice that this guy right here, this exponent here on r, matches this exponent here. Okay, so this is going to be important. Then times the quantity, you have cosine of, remember you add the arguments. So theta plus theta is 2 theta. Then plus I times the sine of theta plus theta, you add the arguments, this is 2 theta. So I want you to notice some things. Again, this 2 here, this exponent matches this exponent here. And then this guy here inside the parentheses, it's multiplying the argument. So the general rule is whatever this exponent is, and this can be any real number. For today, we're just going to work with positive integers. But whatever this guy is, it's going to basically be your exponent on r, and then it's going to be multiplied by your argument inside the parentheses. Okay. Now I can do another one with you just to show you this. So let's say we did something like r times the quantity cosine of theta plus I times the sine of theta. Okay. Let's say now we cube this guy. Okay. So we know that this would be equal to basically this guy times another one, okay? This guy times this guy would give me this guy. So I can go ahead and write r squared times the quantity cosine of 2 theta plus I times the sine of 2 theta, okay? Then multiplied by one more of these. So r times the quantity cosine of theta plus I times the sine of theta, okay? So what is this going to give me? Again, r squared times r is going to be r cubed, so r cubed. Again, notice this exponent here matches this exponent here, okay? So basically after that, inside the parentheses, you're going to have the cosine of 2 theta plus theta is going to be 3 theta, okay? Plus I times the sine of 2 theta plus theta is 3 theta. So again, this exponent here of 3 is going to be your exponent here on r, and then inside the parentheses is going to be multiplying your argument. Okay, and this should make sense because if I'm raising this to the third power or I'm cubing this, then basically I have 3 of these. So I have 1, 2, and then a third one, right? So it makes sense that I have 1, 2, 3 r's. So it's going to be r cubed, right? R times r times r. And then you have this one, and another one. So if you're adding the arguments, you have theta plus theta plus theta, which is 3 theta, okay? So that's what's going to work. If you raise this to the 4th power, you see the same thing, 5th power, 6th power, whatever you want to do, any real number. Okay, so formally, this is our theorem here. You can write this down for your notes. Basically, if you have some complex number in polar form, so let's say r times the quantity cosine of theta plus I times the sine of theta, and this is raised to some real number n, okay, again, we're going to use just positive integers today, then basically you can say it's r to the power of n times the quantity, you have cosine of n times theta plus I times sine of n times theta, okay? So this n is going to be multiplying your argument, and it's also going to be your exponent on r, or the absolute value of that complex number. Again, for the shorthand, remember this is the c, the I, the s. That's where this abbreviation comes from. So we have r to the power of n, and then you have this cis, the cis, some people say, and then we have n times theta. All right, let's jump in and look at an example. So we're going to start with something very, very easy. So we have the negative of 5 times square root of 3 over 2 plus 5 halves I, and this whole thing is being squared. Now, obviously this is in rectangular form, and since this is just being squared, you could expand this and just perform the operation that way. But what we're going to do is use our little theorem. So we're going to first write this in polar form, then we'll use the theorem, okay? So I'll say this is equal to, I'm going to put my r times the quantity cosine of theta plus I times the sine of theta, okay? And this is going to be squared, okay? So I'm going to fill out my r and my theta. So to get those, remember, your r, okay, which is the absolute value of the complex number, is the square root of, you're going to take your real part, which is the negative of 5 times square root of 3 over 2, and you're going to square this, and then plus you're going to take your imaginary part, which is 5 over 2, okay, and you're going to square this. So let me scroll down and get some room going, and we'll come back up in a minute. Basically, if I have negative 5 times square root of 3 over 2 squared, the negative 5 squared is 25. The square root of 3 squared is 3. 2 squared is 4. So this is 75 over 4. let's just replace this and put 75 over 4. And that is a terrible 5, so let's fix that. And then the 5/2 squared is just 25 fourths. So let's put plus 25 fourths. Now 75 plus 25 is 100, and 100 divided by 4 is 25, okay? And obviously 25 is a perfect square. Square root of 25 is 5. Okay, so let's say this is 5. Now, let me come up here just a little bit. So let me scroll up just a little bit. And I'm going to erase this r, and I'm going to put a 5 in there for the actual value. And now I need to figure out what theta is. So lots of ways to think about this. Remember, your tangent of theta, if you're thinking about this as x plus yi, well, it's going to be y over x, okay? If you're thinking about this as a plus bi, then it's b over a. It's the imaginary part over the real part, okay? But you have to be careful about this because when you use your inverse tangent function, you're only going to get something in quadrant 1 if this guy's positive, and something in quadrant 4 rotating clockwise if this guy's negative. Okay, so you got to be real careful here. So let's come up and think a little bit about this. So the y part is 5/2. Okay, so that's 5/2. Then I'm dividing by a fraction, so I'm going to multiply by the reciprocal. The x part, or the real part, is going to be the negative of 5 times square root of 3 over 2. I'm going to flip that, so I'm going to put 2 over 5 times square root of 3. Okay, I'm dividing fractions, that's why I did that. Okay, so what I would see here is that this would cancel with this, and this would cancel with this. So I have the negative of 1 over the square root of 3. Rationalize the denominator. This is square root of 3 over square root of 3. And so this gives me the negative of, you have the square root of 3 over 3. Okay? So let's think about this for a moment. If I type this into my calculator, okay, as the inverse tangent of this guy, I'm going to get something in quadrant 4, and I'm also going to get a negative angle. Okay, so it's going to rotate clockwise. That is not what I want. Okay? So what I'm going to actually do is I'm going to do the inverse tangent of, I'm just going to make this positive, so square root of 3 over 3. This is going to give me my reference angle, okay? So if I punch this into the calculator, I get pi over 6, okay, if you want to work with radians, or you get 30 degrees if you want to work with degrees. Now, this is not my answer because I'm not in quadrant 1. Okay, let's get rid of this. We don't even need this anymore, okay? Let's think about where we are. If you were to graph this complex number on the complex plane, then basically you think about the fact that this is negative, so the real part's negative, and this is positive, right? So this is positive. So from the origin, I would go to the left and I would go up. That puts my complex number in quadrant 2, okay? So in quadrant 2, I want an angle with a reference angle of pi over 6 or 30 degrees, okay? So basically you can say theta is equal to, you could do pi minus your pi over 6, okay? And I can do 6 pi over 6 to get a common denominator. So this is 5 pi over 6, which is 150 degrees, right? If you wanted to do this with degrees, you do 180 degrees minus 30 degrees. So again, it's 150 degrees. So let's do 5 pi over 6. So 5 pi over 6. So that's the tedious part. So let's just erase this and this and go 5 pi over 6. Of course, you can put 150 degrees in there if you feel more comfortable with that. That's up to you. Okay, so now that we have this done, finding our result here is really easy, right? Using our little theorem, this r value here is raised to this power. So 5 is squared. 5 squared is 25. That's easy. Then times the quantity, the cosine of, this gets multiplied by this exponent. So we'll have, let me do this in a different color, 2 times 5 pi over 6, okay? Then plus, let me return to this other color, so plus your I times the sine of, again, it's going to be 2 times 5 pi over 6. Okay, that's all it is. It's very, very simple. Most of the work is just putting it in polar form. So once we have this, we can think about, okay, well, this would cancel with this and give me a 3. This would cancel with this and give me a 3. So this is going to be 25 times the quantity. You have your cosine of 5 pi over 3, okay, plus I times the sine of 5 pi over 3, okay? And 5 pi over 3 is 300 degrees if you want to write it like that. Again, up to you. Now, this is the answer in polar form. If you want to put it in rectangular form, again, it's all over the place in terms of what your teacher would ask for. Let's just get a little quick practice with that. So the cosine of 5 pi over 3, again, the reference angle there is pi over 3, okay, or 60 degrees. So the cosine of pi over 3 is going to be a half, right? And cosine in quadrant 4 is going to be positive. So this equals 1/2. Now the sine of 5 pi over 3, again, pi over 3, if you think about the sine of pi over 3, well, that's going to be square root of 3 over 2, but we're in quadrant 4, so sign is negative. So this is the negative of the square root of 3 over 2, okay? So let's go ahead and replace these. I'll go ahead and say this is equal to 25 times, I'll say this is 1/2. So this is going to be 1/2, and then plus, you have I multiplied by, this is going to be the negative of the square root of 3 over 2. Probably better to kind of switch this around here, and then maybe scooch this down a little bit for formatting. And let's close this down, okay? So let's go ahead and distribute this 25 in. So this would be 25 over 2. And then basically I have plus negative here. Might as well just write minus. It's a little bit easier. I'll say minus 25 times square root of 3 over 2. Now you can put your I out here, and then sometimes people put the I there. It's really up to you. It's very clear here that it's not under the square root symbol, so I would just leave it like this. So this would be your answer in rectangular form, your 25 over 2 minus 25 times square root of 3 over 2, and then times I. All right, let's look at another example. So this one I'm going to give it to you in polar form, make it a little bit quicker. So we have 2 multiplied by the quantity cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. And this whole thing is raised to the 5th power, okay? So if it's in polar form already, it's super easy, right? This R value here, this 2, is going to be raised to the 5th power. So you have 2 to the 5th power. We know that's 32, but we'll just simplify that in a moment. Then inside the parentheses, you'll have your cosine of, again, this exponent here of 5 is going to be multiplied by the argument. So 5 times 7 pi over 4, okay? Maybe make these parentheses a little bit bigger. Then we'll go plus I times the sine of 5 multiplied by the 7 pi over 4. Let me close the parentheses there. So we'll say this is equal to, let's go ahead and say this is 32, right? 2 to the 5th power. Then times the quantity. 5 times 7 is 35. So this would be the cosine of, we'll say, let me make that S a little bit better. So we'll say this is 35 pi over 4. And then we'll say plus I, so plus I, times the sine of 35 pi over 4. Now again, some teachers don't care. You can leave this as your answer if they say we want it in polar form. That's really up to you. If you need to put it in rectangular form, it's kind of hard to do that with 35 pi over 4. I mean, I know we can use calculators, but if you wanted to think about this off the unit circle, for myself, I always like to put it between 0 and 2 pi, with 0 included and 2 pi not, okay? So if you think about 35 over 4, forget about the pi for a second, 35 over 4, that's really close to 36 over 4. 36 over 4 is 9, okay? So that tells me if I think about 2 pi, 4 pi, 6 pi, 8 pi, okay, I would want to subtract 8 pi off to get myself a coterminal angle. So if I did 35 pi over 4 minus 8 pi, of course I could write this as 32 pi over 4, 32 pi over 4, this is 3 pi over 4. Okay, so that looks a little bit easier to work with, so I'm just going to change this. Again, some teachers require it, some don't care. So 32 times the quantity cosine of 3 pi over 4. Let me make that a little bit better, okay? Then plus I times the sine of 3 pi over 4. Okay, so that's done. So if you want your answer in polar form, again, this one if your teacher doesn't care, this one if they do, okay? If you want your answer in rectangular form, well then again, I've got to go through and figure out, well, what is cosine of 3 pi over 4? And what is sine of 3 pi over 4? So if you're not used to working with radians, if you haven't memorized your unit circle, this is 135 degrees. So you know this is in quadrant 2. So sine is positive, okay? And this guy is negative. And remember, with 135 degrees, you have a 45-degree reference angle, or in terms of radians, it's pi over 4, okay? So for both of those, it's square root of 2 over 2 if you think about pi over 4, right? But this one's negative and this one's positive. So this would be the negative of the square root of 2 over 2. And this would be positive square root of 2 over 2, okay? So we would say that you have equals, I'll go 32 times the quantity. I'd have the negative of the square root of 2 over 2. And then plus, you'll have your square root of 2 over 2 times I. Okay, again, the I gets changed around based on what book you're looking at, what teacher you're working with. Sometimes they put it out in front there. It's really up to you. So what I'm going to do here is just say that 32 is multiplied by this. 32 divided by 2 is 16. So this would be negative 16 times square root of 2. Okay, plus 32 times this. The 32 divided by 2 is 16. So I'm going to say 16 times square root of 2, and then times I. Now again, this is all over the place in terms of how the formatting goes. Typically with this, you'll see 16i and then times the square root of 2. Again, you don't want to think that it's underneath this square root symbol, so that's why this is done, okay? So this would be your answer in polar form right here, okay? And then in rectangular form, we say negative 16 times square root of 2 plus 16i times square root of 2. All right, so now let's talk about the roots of complex numbers. So I'm going to use this first example here to derive a little formula we can use. If you don't want to watch it because it's a bit tedious, you can just skip ahead to where we're doing the examples. So first and foremost, every non-zero complex number is going to have exactly n distinct complex nth roots. So you might read this in your book and think, what in the world does that mean? Well, what it means is that every given non-zero complex number is going to have exactly 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, so on and so forth. So what we can do is use this example here to come up with a little formula, okay? Let's say that I asked you to find the 3 complex cube roots of this number, okay? What does that mean? Well, let's just go back to regular numbers. Let's say I had just the number 8, okay? So the number 8. What if I wanted to find the cube root of that? Well, I'm looking for a number that when cubed gives me this number, okay? So we know this is 2, right? So 2 cubed gives me 8. So I'm going to do the same thing. I'm going to be looking for a number that when cubed produces this number here, okay? So all I'm going to do, let me just rewrite this. So I'll just say that 3 times the quantity cosine of, let's say, 45 degrees plus the I times the sine of 45 degrees is going to be equal to, again, I'm just going to take a generic complex number in polar form. So I'm going to say r times the quantity cosine of, I'm going to use alpha here instead of theta. So plus, I'll do I times the sine of, again, I'm going to use this alpha, okay? So now I'm just going to raise this to the third power. There is nothing different between this and what I just showed you with 8 being equal to 2 cubed, okay? I'm just taking this number, raising it to the third power. So this number right here is going to be a cube root, okay, of this number because raising it to the third power produces this. Just like 2 is a cube root of 8 because 2 to the third power is 8, okay? It's all it is. So from this point on, what I'm going to do is just simplify things and come up with a little formula, okay? So I'm just going to say 3 times the quantity cosine of 45 degrees plus I times sine of 45 degrees, okay, is equal to, if I use my theorem from earlier, r would be cubed, so r cubed, and then times the quantity cosine of, I'm multiplying the 3 by the argument, so 3 times my alpha there, plus I times the sine of 3 times alpha, okay? So in order for this to be true, you've got to think about the parts of this equation. So this would have to be equal to this, okay? And then this would have to be equal to this, and then this would have to be equal to this, okay? So in other words, r cubed would have to be equal to 3, which tells me if I take the cube root of each side, okay, the cube root of each side, that r is going to be equal to the cube root of 3. Okay, and we'll see this in our little formula in a moment. For right now, this is what we have. Okay, so let me bring this up here so that's out of the way. And then the next piece would be that the cosine of 45 degrees is equal to the cosine of 3 times alpha. Okay, and then also the sine of 45 degrees is equal to the sine of 3 alpha. Okay, so let's think about this for a moment. We know about coterminal angles, okay, and we know that, let's say the cosine of 45 degrees has the same value as the cosine of, if I added 360 degrees to that, so if I said the cosine of 405 degrees, this would be equal to the cosine of 45 degrees. And you can pause the video and punch into your calculator. You should know that those are equal. It's also equal to the cosine of a negative 315 degrees, okay, if you wanted to do it that way. Okay, so knowing this fact, what we could do is set 3 times alpha, so 3 times alpha, equal to this 45 degrees, okay, plus I'm going to do 360 degrees times some integer k, okay? Now, we don't have to consider negatives. I'm going to show you how solutions just keep repeating themselves. I'm just going to work with 0, 1, and 2, okay? And I'll show you that when you get to 3, 4, 5, 6, things repeat. Also, if you go negative 1, negative 2, negative 3, you're just getting repeat solutions, okay? So what I would do here is I would simplify this a little bit, and I would divide both sides by 3, okay? So both sides by 3. So I'd have that alpha is equal to 45 degrees divided by 3 is 15 degrees, okay? Then plus 360 degrees divided by 3 is 120 degrees, and then times k, okay? So to get the values for alpha, you're going to see in our little formula, you plug in, if I'm trying to find the cube root, then I'm going to plug in 0, 1, and 2. Okay, so I start with 0, then I go to 1, then I go to 2. If I was trying to find the fourth root, I would go 0, 1, 2, 3. So it's always 1 less than that number. Okay, so if it's 4, you're going to 3. If it's 5, you're going to 4. If it's 6, you're going to 5, so on and so forth. So let's go ahead and go through and say our first alpha would be 15 degrees plus 120 degrees times 0. So 120 degrees times 0. So this is basically going to be 15 degrees. Then another alpha would be 15 degrees plus 120 degrees times 1. So this is going to be 135 degrees. So 135 degrees. Then our other alpha is going to be 15 degrees plus you're going to do 120 degrees times 2. And this is going to give me 255 degrees. Okay. And then again, we don't need this, but if you did go to 3, so alpha is equal to 15 degrees plus 120 degrees times 3. Well, this is 360 degrees plus 15 is 375 degrees. 375 degrees and 15 degrees are coterminal angles, okay? So if I was to say the cosine of 15 degrees or the cosine of 375 degrees, it's the same, okay? So you don't need to go 3 and 4 and 5 and 6. You're just going to get repeat solutions, okay? So you don't need that. You also don't need to do the negatives because you're just going to get repeat solutions. So let me erase this. So coming back now, let me show you that these solutions work, okay? So let me box this off. Remember, originally we were looking for the 3 cube roots. So the 3 numbers that I could plug in here and cube them and get back to this number. So let me show you with the first solution for alpha. So we have our R value, which is the cube root, okay, of 3. And then it's multiplied by the quantity cosine of alpha. So one of those would be 15 degrees plus I times the sine of 15 degrees, okay? Let me get rid of this one. Then the next one would be the cube root of 3 times the cosine of, it would be 135 degrees plus I times the sine of 135 degrees, okay? Let's get rid of this one. And then your last root here, so the last cube root, would be the cube root of 3 times the quantity, the cosine of 255 degrees plus I times the sine of 255 degrees, okay? So let's get rid of this. Now, if you were to cube each one of these, you're going to get back to this right here. And we can just do it mentally. We don't need to actually go through it. If we cube this number here, again, following that theorem from earlier, this guy right here would be cubed. So cubing the cube root of 3 gives me 3. So it gives me back that number. Then if I multiply 3 times 15 degrees, I get 45 degrees. If I multiply 3 times 15 degrees, I get 45 degrees. So you can see that cubing this first one right here gives us this back. Now, I'll let you do this one and this one on your own. Just cube them. You're going to see that the angle you get in each case is going to be coterminal with this angle here that's 45 degrees. In this case, it would be 405 degrees. And in this case, it would be 765 degrees. Okay, so let's go from our example and make a nice little formula. So if n is any positive integer, and r is a positive real number, and theta is in degrees, then the non-zero complex number, let's say r times the quantity cosine of theta plus I times the sine of theta, is going to have exactly n distinct nth roots given by the following. So we're going to say that we have the nth root, okay, of this r. You saw earlier we were looking for cube roots, so we had the cube root, which was n was 3, of, in our case, it was 3, so it was the cube root of 3, okay? And basically, we're going to multiply this by the quantity. You'll have the cosine of alpha plus I times the sine of alpha, okay? And basically, what alpha is going to be, I'll do degrees first and then I'll do radians. So alpha is going to be theta, okay? So this guy right here, divided by your n. Okay, so you saw earlier, what we had was 45 degrees divided by 3, which gave us 15 degrees, okay? Then plus, you're going to do 360 degrees times k is just some integer, and I'll talk more about that in a second, divided by n. So in our example, you saw 360 degrees divided by 3, okay, which gave us 120 degrees. And then multiplied by k, where basically k is going to be equal to 0, 1, 2, 3. We'll put the 3 dots here to show the pattern continues, and then we'll go n minus 1, okay? So in our case, our n was 3, so we went 0, 1, 2. Then 3 would give us a repeat solution, so would 4, so would 5, so would 6, so on and so forth. Now, if you're working with radians, then you would adjust this formula, and basically instead of 360 degrees, you would just put 2 pi in there, okay, in terms of radians. Nothing else is going to change. So just depending on if you're working with degrees or radians, you would either want to use 360 degrees for degrees or 2 pi for radians. All right, let's go ahead and look at an example. So we want to find all nth roots, okay, and we're going to write our answer in polar form. So we see that n is set equal to 4, so we want to find the 4 fourth roots, okay? So I'm going to start by writing this guy right here, this negative 3 times square root of 3 minus 3i in our polar form, okay? And so let's go ahead and say that the r value would be what? The square root of, we take the negative of 3 times square root of 3, we're going to be squaring that, plus you're going to take your negative 3, okay, we're going to be squaring that. So the r is going to be equal to, we'll say the square root of, negative 3 squared is 9, square root of 3 squared is 3, 9 times 3 is 27. So this is 27 plus negative 3 being squared is 9, 27 plus 9 is 36, so r equals the square root of 36, so r equals 6, okay? So we've got that part down. Let me go ahead and say that in polar form, this negative 3 times square root of 3 minus 3i would be equal to, I'd put a 6 there, times, you're going to have your cosine, okay, your cosine of theta, I'll replace this in a second, plus your I times your sine of theta, okay? So for theta, again, remember that the tangent of theta is equal to, take the imaginary part, so negative 3, over your real part, which is negative 3 times square root of 3. And so with this, we see the negatives are going to cancel, the 3's are going to cancel. So you have 1 over square root of 3. Again, rationalize the denominator, so square root of 3 over square root of 3. So this is going to be what? Square root of 3 over 3. So if I did my inverse tangent, so my inverse tangent here of square root of 3 over 3, let me make that 3 a little bit better. If we punch this into our calculator, you're going to get 30 degrees, or pi over 6 if you want to work with radians. Let's just work with degrees. So I'm going to say this is 30 degrees. So this is my reference angle. So let me erase this. And let's think about where this complex number would be if we graphed it. So this is negative, and so is this, right? So I have a negative real part and a negative imaginary part. So from the origin, I would go to the left, and then I would go down, okay? So that means I'm going to be in quadrant 3. So my theta here would be 180 degrees plus the reference angle of 30 degrees, which is 210 degrees, okay? So I can just erase this, and I'll go ahead and put 210 degrees there. So 210 degrees. Once you have this in polar form, it's just a matter of plugging into your formula. You want to do your nth root of r. So in our case, n is 4 and r is 6. So we want the fourth root of 6. So we want the fourth root of 6. And you're going to have 4 of these, but I'm just going to start out with the first one, okay? Inside of here, what are we going to have? We're going to have the cosine of, again, we call this alpha plus I times the sine of alpha, okay? And alpha, since we're working with degrees, alpha is going to be equal to, you have your theta divided by n. In this case, the n is 4. Plug that in a second. Plus, you have your 360 degrees divided by n times k, where we say that k is equal to, in this case, because it's 4, it's going to be 0, 1, 2, and 3. Okay? So you just go up to 1 less than whatever n is. That's all it is. So in our case, let's just plug this in. So n is going to be 4. So let's erase this and put 4 in each case, okay? And then theta is coming from here. So it's 210 degrees, okay? So let's put 210 degrees here. So if I divide 210 degrees by 4, it's going to give me 52.5 degrees. So 52.5 degrees. And then 360 degrees divided by 4 is going to give me 90 degrees, okay? So 90 degrees. So basically, to set this up, the first one would be, again, if this guy was 0, plug that in, this is gone. So you just get 52.5 degrees. Okay, so you can put that in there. So 52.5 and 52.5. Now, you can pause the video and you can raise this to the 4th power, and you'll see that you get back to this guy right here. Okay, and then, of course, you can convert that back into rectangular form if you wanted to get back to that original form we started with. Okay, but let's go ahead and keep going. And basically, let me drag this down just a little bit. And I'm going to slide my screen just a little bit down, okay? And basically, now I'm going to do the fourth root of 6 times the quantity. I'll do the cosine of, and then I'll leave that blank for now, and then I times the sine of. And let me leave that blank for right now. So the next one would be, this guy would be 1 now. Okay, so I'm going to plug in a 1. So basically, 90 degrees times 1 is 90 degrees, and 90 degrees plus 52.5 degrees is going to be 142.5 degrees. And I forgot my degree symbol here and here, so let me put that in. So 142.5 degrees. Let me make that decimal point a little bit better. So from here, all I'm going to do is add on 90 degrees, okay, 2 more times. So I can just get rid of this, okay, once you understand the pattern. And basically, I can just copy this. And so 142.5 plus 90 is 232.5. So this would be 232.5 degrees. And this would be, again, 232.5 degrees. And then add 90 degrees again, and you get 322.5. So 322.5 and 322.5, okay? So this would be your 4 fourth roots for that number. I'm leaving these in polar form. All right, let's take a look at another example. I think this is going to be pretty easy for us at this point, but I want to throw something in here. Sometimes your book will ask you to graph the roots on the Argand diagram or the complex plane. So let's go ahead and do this. So we have negative 8 plus 8i times square root of 3. Again, n is going to be 4. So I'm looking for the 4 fourth roots. Now, again, this is given to us in rectangular form, so I need to convert it into polar form first, okay? So the r value times, again, the quantity cosine of theta plus I times the sine of theta. So let's do this quickly. So r is going to be what? The square root of negative 8 squared is 64. And then if you have 8 times square root of 3 being squared, it's 64 times 3, which is 192. Okay, so you're adding those two together. And that's going to give me 256. If I took the square root of that, I would get 16. Okay, so let's just erase this and put 16 here. Then for theta, it's going to be where? The real part is negative, so I'm going to the left. The imaginary part is positive, so then I'm going up. So from the origin, if I go to the left and I go up, I'm going to be in quadrant 2. Okay? So let's say that theta will be equal to 180 degrees minus my reference angle. And the reference angle here, let's go 8 times square root of 3. And I'm going to divide that by, forget about the negative, let's just do 8. This is going to cancel with this, so this is square root of 3. Okay, so I'm going to say the tangent inverse of this guy right here is going to give me 60 degrees, okay? So if I subtract 60 degrees away from 180 degrees, okay, because this is my reference angle in quadrant 2, well, it's going to be 120 degrees, okay? So that's my theta. Let's get rid of this. Let's put in 120 degrees and 120 degrees. Okay, so that's pretty quick. All right, so from here, I need to get the 4 fourth roots. So in each case, I'm going to take the 4th root of 16, right? Because again, it's the nth root of r. So n is 4, r is 16. So the 4th root of 16 is 2, right? Because 2 to the 4th power is 16. So I'm going to put 2, 2, 2, and 2, okay? Let's go ahead and set this up in each way. So cosine, 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 and then cosine, okay? So what's going to go here, 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 and here? Remember, when you think about the formula, if you call this alpha, it's equal to, again, you take theta, okay, which in this case is 120 degrees, and you divide it by n. So you divide it by 4. So in this case, that would be 30 degrees, okay? Then plus you have your 360 degrees times your integer k divided by your n. So 360 degrees divided by, in this case, it would be 4, would be 90 degrees, okay? So this would be 90 degrees times k. So for the first instance, this would be 30 degrees. So let's go ahead and put 30 degrees here. I'll fill out the rest in a moment, okay? In the next instance, it's going to be plus 90 degrees. So this would be 120 degrees. Then plus 90 degrees. So this would be 210 degrees. Then plus 90 degrees. So this would be 300 degrees. So let's get rid of this. And let's put our plus, 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 I, and I. And then the sine, the sine, the sine, and then the sine of 30 degrees, close that down, and this will be 120 degrees, close that down, and then 210 degrees, close that down, and then 300 degrees, okay? So these are our 4 fourth roots, okay, for this number in polar form. Okay, so how would we go about graphing these complex roots? Well, basically, each of these can be represented as a position vector in the complex plane. So notice that your magnitude in each case is 2. Okay, so 2, 2, 2, and 2. So what you could do to represent that is you could have a little circle with the center at the origin and where the radius is 2. Okay, so each one of these as a vector is going to have an initial point at the origin and a terminal point that's going to touch that circle that you drew. Okay, and then in terms of the direction angle for the vector, you just get it from here. So the first one would be 30 degrees, the second would be 120 degrees, the third one would be 210 degrees, and the fourth one would be 300 degrees, okay? So these guys are going to be spaced 90 degrees apart, okay? So equally spaced 90 degrees apart. So if we go to our little coordinate plane, and I know that most people put imaginary here, so you can put that if you want. So you can put imaginary, and then for this, you could put real. But again, if you write this as x plus yi, then x could still be your real axis, and y could be your imaginary axis. It's really up to you or your teacher, okay? So I'm just putting it this way. So when we think about this, again, the first solution was 2 times the quantity of the cosine of 30 degrees plus I times the sine of 30 degrees. We abbreviated it here. But you can see that I have a position vector. The initial point is at the origin. The terminal point is going to touch this little circle that I drew, okay, with a radius of 2 and a center at the origin, okay? So you see that this is a 30-degree angle, okay? And then if we go another 90 degrees here, so this is another 90 degrees, you can see that little 90-degree symbol there. Basically, I'm going to get to my next solution. So the angle here is 120 degrees. Again, if I started here, 30 degrees plus 90 degrees gives me 120 degrees, okay, for the whole thing. And then basically, you can see that it touches, again, our little circle. If we keep going around, this is another 90 degrees, and then this is another 90 degrees. Okay, so it keeps putting you to another solution. So this angle here, if I started here and went all the way to here, this is 210 degrees. If I started here and went all the way around to here, this is going to be 300 degrees. Okay, so that's basically how you can sketch the graph if you're given this as an assignment. Again, just take your magnitude. Okay, in each case, ours was 2, and draw yourself a little circle with the center at the origin and the radius of that number. Okay, in our case, it's 2. Then what you want to do is have position vectors. So they start at the origin, and their terminal point is going to be on that circle, and your direction angle in each case is given by the angle. So here it's 30 degrees, here's 120 degrees, here it's 210 degrees, and here it's 300 degrees. All right, so let's wrap up the lesson and look at another example. Here we're going to be solving a simple equation using the roots of a complex number. Okay, let's say we saw something like x cubed minus 27, and this was equal to 0. The first thing, we know that since this polynomial here is of degree 3, okay, we have this exponent of 3 here and none higher, well, we know we're going to have exactly 3 complex solutions for this equation. Okay, that's the fundamental theorem of algebra. So how could we use the roots of a complex number to solve an equation like this? Well, the first thing is I could add 27 to both sides, okay? And I could set this up and say, really, this is x cubed is equal to 27. Okay, let's pause and think about this for a minute. I am looking for a value that I can plug in here and cube it and get 27. So in other words, what number cubed gives me 27? So if I found the 3 complex cube roots of 27, I could plug them in for x, and I would have a true statement, okay? So you might be thinking, well, 27 is a real number. Remember, all real numbers are complex numbers. The real number system is a subset of the complex number system. I can write 27 as 27 plus 0i, okay? So with this format here, I can also write this in polar form. This is really easy to do. If you think about the r value, it's just going to be 27, okay? Because you think about this as, okay, well, r is equal to the square root of 27 squared plus 0 squared. 0 squared, you can just get rid of that, okay? And the square root of 27 squared is just 27. So our r value is 27. Then, in terms of this inside part, it's easy as well. So you'd have the cosine of, again, theta plus I times the sine of theta. So you don't need to do any inverse tangent function here or anything like that. Just think about this complex number if you graphed it on the complex plane. You would simply start at the origin and go 27 units to the right, okay? So there's no movement at all vertically, right? You're on the x-axis or the real axis if you want to think about it that way. So really, this is going to be a 0-degree angle, right? I haven't moved off the real axis. So I'll just go ahead and put this as a 0-degree angle. Okay, and that's all it is. So this is me writing the number 27, first in rectangular form, and then in polar form. Now, in order to find my 3 complex cube roots, I'm going to start with my simple little formula. So I have the nth root of r. So in this case, n is 3, right, because I'm looking for a cube root, and r is 27. Well, the cube root of 27 is 3, right? 3 times 3 is 9, 9 times 3 is 27. Okay, so I can set this up. I know I have 3 of them, so I'll go 3, I'll go 3, and I'll go 3, okay? Let me just write all this out. So we have cosine, cosine, and cosine, and we're going to use alpha, we're going to use alpha, and alpha, and I'll replace this in a moment. So plus, plus, and plus, I, and then sine, sine, and sine, okay? And I'm going to use alpha again, and alpha again, okay? So again, these are all going to change based on that input for k. So to find alpha, let's go ahead and set this up over here, put a little border here. To find alpha, the idea is that it's theta, whatever this is, in this case it's 0 degrees, divided by n, which in this case is 3, okay? So 0 degrees divided by 3 is just 0 degrees. So this is 0 degrees. You can put it there or leave it off. It doesn't matter. It's not going to change anything. I'm just going to leave it for the sake of completeness. So then plus you have 360 degrees divided by n. In this case, that's 3. So this is 120 degrees, okay? And then times your k. Now, k is going to be 0, 1, and 2. Basically, your pattern is what? It's 0, 1, 2, 3, n minus 1. Let me put a comma in there to make that complete. And basically, you have 3, so 3 minus 1 is 2. So in this case, we would only go up to 2. Okay, so that's how that works. So I'd start with a 0 there. And of course, 0 degrees plus 0 degrees is just 0 degrees. So the first guy here is just going to be 0 degrees. So I can put that in here, and that should make sense. If I cubed this, 3 cubed would be 27, and then you would basically have 3 times 0 degrees, which is still 0 degrees, and 3 times 0 degrees, which is still 0 degrees. So in polar form, I would be right back to this here. 27 times the quantity, cosine of 0 degrees, plus I times the sine of 0 degrees, which again in rectangular form is this, and written just as a real number is this, okay? So then the other one, I'm just going to add 120 degrees each time. If I plugged in a 1 there, this would just be 120 degrees. So 120 degrees, 120 degrees. Add another 120 degrees. If I plugged in a 2 there, this would be 240 degrees. So 240 degrees and 240 degrees, okay? So these three numbers here in polar form, these three complex numbers in polar form, if you cube them, they would each give you 27. Now, typically, if you were in an algebra class, you would not give this as your solutions, right? You would want to convert this back into rectangular form, okay? So how would we do this? The cosine of 0 degrees is going to be 1, and the sine of 0 degrees is going to be 0. So basically, you would have 3 times 1, which is 3. So I would say x is equal to 3. Okay, that would be my first solution. For this one, the cosine of 120 degrees and the sine of 120 degrees, let's think about this. There's a 60-degree reference angle here, 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 and here, right? 120 degrees, 240 degrees, you have a 60-degree reference angle. So the cosine of 60 degrees is going to be 1/2. And the sine of 60 degrees is square root of 3 over 2, okay? So it's just a matter of getting the signs right. Remember, sine is going to be positive in quadrants 1 and 2, and 120 degrees is in quadrant 2. Cosine is going to be positive in quadrants 1 and 4, okay? So basically, cosine is negative in each case, because this is quadrant 2, this is quadrant 3, and sine is positive here and negative here, okay? So to get my solutions, let me write this out. I'm just going to scroll down a little bit so we have some room. For this one, I would have what? 3 times, this would be the quantity, negative 1/2, plus this guy is going to be square root of 3 over 2, okay, times I. So if I go ahead and distribute the 3 into each term, I would have negative 3/2, and then plus my 3 times square root of 3 over 2 times I. Okay, so that's another solution. Then the other one, let me just go ahead and keep this as negative, and I'm going to change this to negative now. So basically, you would have negative 3/2 again, and then minus the 3 times square root of 3 over 2, and then times I, okay? So I would write this in a more compact form. I would just do plus or minus here and get rid of this. That way you can more cleanly write your 3 solutions. So if you were in an algebra class and they gave you this equation, you would want to give this as a solution. Now, in this particular case, this is probably not the fastest method to do this, but it's one such method that you can get a solution. Now, let's think about this graphically. If I wanted to show these solutions, again, I'm going to do this in polar form, okay? So on the Argand diagram or the complex plane, again, the magnitude is 3 in each case. So that's the length of your vector. So if you're making a circle, okay, with a radius of 3 that is centered at the origin, each one of these vectors is going to touch that circle, okay? That's going to be your terminal point that lies there, okay? And then your direction angle for your vector is going to be 0 degrees, then the other one's going to be 120 degrees, then the other one's going to be 240 degrees, okay? All of them are position vectors, so they start, or their initial point is at the origin. So graphically, this is a rough sketch of this guy. Again, I have a little circle that's drawn, and the radius is 3, and the center is at the origin, okay? Then you have your 3 position vectors. Notice that they're all going to have an initial point at the origin. The terminal point in each case is on that circle, again, where the radius is 3 and the center is at the origin. So your first angle is 0 degrees. Okay, it's given by this 3 cis 0 degrees. Again, this is the abbreviation. The second angle is 120 degrees. Okay, so we come from here, we rotate 120 degrees, and now we have that vector there. Okay, and the terminal point's there. And then the last one, if I rotate around here, this is going to be a 240 degree angle. Okay, so that's how you would sketch the graph of this guy. You'll notice that these guys are equally spaced 120 degrees apart, right? 120 degrees, this is 120 degrees, and this is 120 degrees as well. So this is how you can graph your solutions if you're asked to do them. Again, figure out the magnitude or the length of the vectors. You're going to sketch yourself a little circle, okay, with a radius of that number. In this case, it's 3, and a center at the origin. So all of your vectors are going to be position vectors, initial point at the origin, terminal point's going to be on that circle, and you just get your direction angle from your roots. So we had 0 degrees, 120 degrees, and then 240 degrees.